Hello there and welcome to Science for Sleep, where curiosity gets cozy and astronomy takes the scenic route toward rest. Tonight's quiet journey is going to guide us far beyond the hum of our daily clocks and even past the familiar sprawl of our Milky Way. We are heading towards something so unusual, so rare in its appearance, that astronomers themselves had to pause, scratch their heads, and admit they weren't quite sure what they were looking at. The sky is full of galaxies after all. Spirals with their swirling arms, ellipticals glowing like giant eggs of light, irregular ones that look like spilled starlight smeared across black velvet. But among all of these cosmic forms, there is one that seems almost too perfect, too geometrically precise, and far too strange to fit into the categories that scientists usually rely on. It is called Hoag's object, and if Galaxies had a family photo, this one would stand out like a guest who showed up in an outfit no one else thought to wear. Before we step into its circle of light, I wonder, where are you listening from tonight? Maybe you're curled up in bed with a cool breeze pressing against the curtains. Perhaps you're on the sofa after a long day, letting the stillness settle into your shoulders. Maybe you're half awake, drifting toward dreams while the universe waits just outside your window. If you glance at the clock right now, what time does it read? The numbers marking this moment for you are not the same as the numbers ticking away for someone listening halfway around the world. Yet here we are, meeting in the same cosmic second, sharing a thought about a galaxy millions of light years away. It's funny how even the most distant things can bring us together in the present. If this kind of gentle exploration feels like a small refuge for you, a space to unwind while still learning something remarkable, I'd be grateful if you gave the video a like, or perhaps even subscribed. It helps this corner of calm reach more people who might need it, and it allows me to keep making these voyages for nights like this one. So let's slow our thoughts, soften the day behind us, and begin. Imagine a circle hanging in space. Not the faint suggestion of a curve that you sometimes see in spiral galaxies, not the elongated glow of an elliptical, but a ring. A ring so precise that it looks drawn by hand, as though some cosmic artist used a compass to mark out the stars. At the very centre of this ring, not attached to it, not connected by graceful spiral arms, but entirely separate, sits a golden ball of older stars. And between that glowing hub and the brilliant blue circle around it, there is a void, an empty black gap that only deepens the mystery. It is this peculiar arrangement that astronomers call Hoag's object, a galaxy that seems to break the usual rules of how galaxies grow, collide, and take shape. When you first see a picture of it, the natural response is disbelief. It looks too clean, too mathematical. A perfect golden core, a perfectly round ring, and a perfectly dark space in between. If you were told it was computer-generated, you might believe it. Yet it is out there, suspended in the northern constellation of Serpens, about 600 million light-years away. That number is almost impossible to wrap your mind around. Light itself, the fastest traveller in the universe, takes 600 million years just to cross that distance from Hoag's object to us. When we look at it through telescopes, we are seeing it as it was long before humans walked on Earth, before even the dinosaurs had their reign. The name might sound modest, almost like a footnote, but it comes from the astronomer who first noticed this strange circular form in 1950. Arthur Hoag was an American astronomer who, at the time, wasn't even looking for galaxies like this. He was surveying stars, cataloguing their properties, and while doing so stumbled upon this bizarre ring of light. At first, he wasn't sure what it was at all. He considered whether it might simply be an optical trick, a strange nebula, or perhaps some artifact of the telescope. But the more carefully it was observed, the clearer it became that this was something real, something that didn't quite match the patterns in the textbooks. What makes Hoag's object so captivating is that galaxies don't usually arrange themselves this way. There are ring galaxies, yes, but their rings often come from collisions, when one galaxy plunges through another and triggers waves of star formation that ripple outward. Those rings are typically uneven, warped, or filled with connecting bridges of material. Hoag's object, however, is unnervingly tidy. The central bulge of older reddish stars sits calmly in the middle, while the outer ring gleams with hot young blue stars as though the two components belong to different worlds entirely, and that empty gap between them only raises more questions. Why would a galaxy form with a vacant space in its middle, a dark moat dividing its populations of stars? To appreciate why this is strange, it helps to know what astronomers expect. Most galaxies are bound together by gravity in patterns that are messy, tangled, and layered with history. Spirals like our Milky Way have arms full of dust and gas, where stars are continuously being born, while their centres often hold bulges of older stars. Elliptical galaxies are like giant glowing eggs, smoother and less structured, but still without rings. Irregular galaxies have no real shape at all. Hoag's object, with its circular ring separated from a central ball, does not fit easily into any of these categories. It looks more like a cosmic target painted against the night. When Arthur Hoag published his discovery, he admitted that he wasn't sure what could explain it. Over the decades, astronomers have offered ideas. Some suggested it might have formed after another galaxy passed directly through it, sparking waves of star formation in the outer regions. Others propose gravitational lensing, where a massive object bends light from something behind it, creating a ring-like illusion. But closer inspection ruled out lensing. This was no mirage. It was a galaxy in its own right, standing alone in its perfection. And so it lingers as one of the great puzzles of extragalactic astronomy. The more powerful our telescopes become, the clearer its image grows, and yet the explanation remains elusive. The Hubble Space Telescope captured breathtaking pictures of Hoag's object, revealing the fine details of its blue ring and golden core, and even spotting another galaxy in the background that just happens to line up in the middle, visible through the transparent space between the inner and outer regions. As though this galaxy was already strange enough, the universe decided to put another, smaller cosmic circle within its circle, like a painting hung inside another frame. You might wonder why astronomers care so much about one odd galaxy, when there are billions upon billions of galaxies in the observable universe. The reason is that outliers teach us the most. When a galaxy refuses to follow the usual rules, it exposes the limits of our understanding. If we can't explain Hoag's object, what else are we missing about the way matter organizes itself across the cosmos? It's like finding a snowflake that isn't just intricate, but perfectly round, unlike any other. Suddenly you have to ask whether your entire theory of snowflakes is incomplete. As we settle deeper into this story, it's worth keeping in mind that astronomy often progresses by chasing anomalies. Astronomers notice something that shouldn't be there, something that defies the categories, and then spend years or even decades unravelling its meaning. In that sense, Hoag's object is not just a curiosity, it is a signpost pointing toward gaps in our knowledge. It reminds us that even in a universe we think we've mapped with spirals and ellipticals, there are still surprises waiting to redraw the map. And while the scientists debate, the rest of us can simply marvel. There is something soothing about the idea that in the endless sprawl of the cosmos, a galaxy chose to arrange itself into a perfect ring, like a jewel suspended in black velvet. Perhaps it is just physics at work, or perhaps it is a reminder that nature has a way of making art even in the vast silence of space. When astronomers first turned their telescopes toward the peculiar object that would one day carry Arthur Hoag's name, they weren't expecting to stumble upon one of the strangest puzzles in galactic astronomy. The year was 1950, and the instruments of the time were nothing like the digital eyes we now point at the sky. Observations were carried out with glass photographic plates, where faint smudges of light collected after hours of exposure, leaving behind ghostly impressions of the heavens. It was during one of these careful surveys that Arthur Hoag, a scientist who spent much of his career studying stars and their light, noticed something unusual. It didn't look like the galaxies he was used to cataloguing. Galaxies were supposed to show familiar structures, the thick oval of an elliptical, the graceful winding arms of a spiral, or perhaps the messy sprawl of an irregular. But here was a nearly perfect circle. At the centre was a small, glowing sphere of stars, compact and concentrated. Surrounding it at a distance was a luminous ring, and between the two there was nothing. No wisps of gas bridging the gap, no spiral arms stretched like threads, only darkness. To Hoag, it looked less like a galaxy and more like a celestial target, a bullseye imprinted on the night. At first, he considered whether it might simply be a planetary nebula. Planetary nebulae are shells of gas cast off by dying stars. Through older telescopes, they often appeared as circular forms surrounding a bright core. That seemed like a plausible explanation, but the scale of this object told a different story. The faint ring was far too large to belong to a single star's outflow. It extended across tens of thousands of light years, more consistent with the dimensions of entire galaxies. Whatever it wasn't the familiar death shroud of a sun-like star. So what was it? In his early notes, Hoag himself admitted he wasn't sure. He cautiously labelled it as a peculiar object, leaving its classification open. He might not have realised at that moment just how peculiar it would turn out to be, but the image stuck with him. Unlike so many fuzzy smudges in astronomy, this one had geometry, symmetry, and above all mystery. The discovery didn't cause much of a stir at first. Astronomers are used to oddities, and the middle of the 20th century was a time of many new catalogue entries, each one waiting for more powerful telescopes to reveal their nature. Hoag's object was logged and noted, but it remained obscure for decades. It wasn't until later, as astronomy advanced with space-based observatories and higher resolution detectors, that the true strangeness of this galaxy became undeniable. Still, there's something almost comforting about the way it was found. Arthur Hoag wasn't setting out to solve cosmic puzzles or rewrite the structure of galactic evolution. He was simply surveying, collecting data, and keeping careful records. It's a reminder that discovery often arrives quietly, not with trumpets or fanfare, but with the careful eye of someone willing to notice when something looks a little off. Think about the patience it took in that era. Each photographic plate had to be prepared, exposed, and developed. Observers sat through long nights guiding their telescopes, keeping the stars steady in view. The reward was a delicate sheet of glass bearing faint marks of light that had travelled millions or even billions of years to reach Earth. Among those streaks and smudges, most of which looked ordinary, Hoag noticed the perfect ring. He didn't dismiss it. He didn't brush it off as a flaw. He set it aside, described it, and offered it to the community. Without that small act of attention, we might not be talking about it tonight. Looking back, it's striking to realise how many things could have prevented its recognition. The photographic plate could have been scratched, giving the illusion of a ring where there was none. The telescope could have drifted slightly, smearing the light and blending the ring into a blur. Or Hoag himself could have decided it was unimportant. But none of those things happened. Instead, the universe revealed its odd design to a human eye at exactly the right moment. When astronomers later revisited the object with better tools, the details began to emerge. The core was not a young star-forming region, as might be expected if this were a typical ring galaxy produced by collisions. Instead, it was made of older reddish stars, like the settled heart of an elliptical galaxy. The surrounding ring, however, was bright with hot blue stars, the kind that burn fast and fierce, suggesting active star formation. That stark contrast between old and young only deepened the mystery. It was as if two different epochs of cosmic history had been pressed into one design. Hoag's object gradually moved from being a footnote to being an emblem of galactic peculiarity. Astronomers love to classify, to sort the universe into categories, but this one resisted easy filing. And the more it resisted, the more interesting it became. It started showing up in astronomy textbooks, not as an example of a type, but as an example of the exceptions that keep science alive. Even its setting in the sky added to the sense of wonder. Located in the constellation of Serpens, it doesn't reveal itself to the unaided eye. Only with powerful telescopes can its full structure be seen. And yet, once you see it, it's unforgettable. Many amateur astronomers who stumble across images of Hoag's object report the same reaction. Disbelief, followed by fascination. It looks so deliberate, so crafted, that it's tempting to imagine forces at work beyond the usual processes of gravity and gas dynamics. Of course, science sticks to natural explanations, but even natural explanations can feel astonishing. When the Hubble Space Telescope finally turned its gaze toward Hoag's object decades later, the clarity of the image silenced any doubts about its reality. The ring was sharp, the core was distinct, and the gap between them was hauntingly empty. As if to add one last twist, Hubble also revealed a tiny, more distant ring galaxy, perfectly aligned inside the hollow space, peering through like a cosmic cameo. The odds of that alignment are staggering, yet there it is, captured forever in the frame. It's almost as though the universe enjoys playing with coincidence, offering astronomers both a puzzle and a sense of humour. But it all traces back to that quiet night in 1950, when Arthur Hoag was patient enough to notice. That's the beauty of astronomy. Each observation is a conversation with the past. Light left Hoag's object 600 million years ago, travelled silently across intergalactic space, past countless stars and clusters, and finally, one night, landed on a glass plate in the hands of a human being who had the curiosity to look closer. That moment stitched together the story we now continue to tell, and that story is only beginning. Because once a discovery like this enters the scientific record, the real work starts. Astronomers begin to ask, how could this form exist? What sequence of events could build a galaxy like this? Does it represent a rare accident, or does it point to processes we haven't yet understood? The discovery is not the end, it's the invitation. And Hoag's object extended one of the most intriguing invitations of the 20th century. When most people imagine a galaxy, the picture that forms in the mind usually falls into one of a few familiar shapes. The great spirals, like our own Milky Way or the famous Andromeda, stretching their luminous arms across space in curling, graceful arcs. The ellipticals, large and glowing, shaped more like spheres or flattened eggs, smooth in their distribution of stars, lacking the sharp structure of arms but still holding billions upon billions of suns. Or the irregulars, scattered and chaotic, where gravitational encounters have torn symmetry apart and left behind a jumble of starlight. These three categories, spiral, elliptical, irregular, form the basic grammar of galactic astronomy, a way of sorting the overwhelming variety of cosmic systems into manageable types. Yet Hoag's object refuses to sit comfortably in any of them. The first thing that sets it apart is its geometry. Galaxies are messy, even the spirals. Spiral arms are not tidy swirls painted with mathematical precision. They are uneven, clumpy, made of patches where stars are being born in fits and starts. Dust clouds obscure sections, supernovae brighten others, and tidal interactions with neighbouring galaxies tug at their structure, warping them over time. Spirals are beautiful, but their beauty is imperfect, organic, like the grain of wood or the veins in a leaf. Hoag's object, by contrast, is shockingly clean. The outer ring is nearly a perfect circle. Not a stretched ellipse, not an uneven oval, but a ring that seems drawn with a compass. That kind of symmetry is almost never seen on this scale. Then there is the question of the core. In a normal spiral galaxy, the core is connected to its arms by a continuous disk of stars. In an elliptical, the core is simply the galaxy itself, the whole mass forming one glowing ball. Hoag's object has a core that looks somewhat like an elliptical's, a dense yellowish sphere of older stars, but instead of being surrounded by a gradual fall-off of light, it is abruptly cut off. Beyond the core is nothing, just darkness, an empty gap that separates it from the outer ring. That void makes the system feel almost artificial, as though someone carved out a trench around the core and left it empty before setting a bright wreath of young stars around the edge. The contrast between the old central stars and the youthful stars in the ring is another oddity. In astronomy, star formation tends to follow the availability of gas and dust. If a galaxy is still rich in gas, stars can continue to form throughout, producing both young and old populations in overlapping regions. In gas-poor galaxies, star formation dwindles, leaving mostly older populations. Hoag's object somehow manages to keep its young stars confined to the ring, while the core is locked into an older state. The two regions seem to be living separate lives, one ancient and settled, the other still vibrant and restless. That separation makes astronomers wonder what kind of history could have led to such a clear division. Even among ring galaxies, Hoag's object is extraordinary. Most rings form from dramatic encounters. When a smaller galaxy plunges through a larger one, it sets off a ripple of star formation that spreads outward like a shockwave. Those rings, however, are rarely perfect. They tend to be off-center, asymmetric, lopsided, or accompanied by visible remnants of the colliding partner. Hoag's object lacks those scars. Its ring is so round and its core so undisturbed that the usual explanations seem unsatisfying. If a collision did occur, it must have been in an extraordinarily precise way, leaving behind no obvious signs of disruption. Its sheer isolation adds to the enigma. Hoag's object does not sit in a crowded cluster of galaxies where frequent interactions might make unusual shapes more common. It hangs relatively alone, with no obvious nearby neighbour to blame for its peculiar structure. Many galaxies can be explained by their environment. They are stretched by tidal forces, stirred by collisions or blended through mergers. Hoag's object, however, seems to have achieved its form without the influence of a bustling neighbourhood. That makes it difficult to point to any external cause. The scale of the structure deepens the wonder. The outer ring spans about 120,000 light-years across, making it larger than the Milky Way. To put that in perspective, if you travelled at the speed of light, the fastest speed allowed by physics, it would take you more than 100,000 years just to cross from one side of the ring to the other. Contained within that span are billions of young, hot, blue stars burning brightly against the dark backdrop of intergalactic space. The contrast of that luminous outer ring with the golden inner sphere makes the whole object look like a cosmic eye staring outward from the constellation Serpens. Astronomers who study galactic evolution often describe galaxies as living things, with life cycles shaped by growth, collisions, and aging. In that analogy, Hoag's object is a creature that doesn't match the anatomy of its relatives. It's not just unusual, it's as if it skipped chapters in the evolutionary story. It doesn't show the gradual blending of structures that most galaxies reveal. Instead, it shows two distinct parts, as if two different galaxies had been stitched together with invisible thread. What makes this difference even more striking is how stable it seems to be. Over decades of observation, Hoag's object has not shown signs of unravelling or collapsing. The ring remains intact, the gap remains empty, and the core remains separate. If it were a temporary stage of galactic evolution, astronomers might expect to see more galaxies caught in similar transitions. But Hoag's object stands largely alone. Other ring galaxies exist, yes, but few with its degree of symmetry and separation. That rarity suggests either that it is the product of an almost impossibly precise set of circumstances, or that it points to processes we still don't understand. To appreciate just how unusual this is, think of the vast number of galaxies in the observable universe. Estimates run into the hundreds of billions, each with its own shape, size, and history. Out of that unimaginable population, Hoag's object is one of only a tiny handful that look like this. Its odds of appearing at all are slim, and yet there it is, captured in our telescopes, defying the categories. For astronomers, that makes it irresistible. It's like finding a single puzzle piece that doesn't match the picture on the box. You can't just set it aside. You have to figure out where it belongs, or whether the picture itself needs to be redrawn. What makes Hoag's object different, then, is not only its appearance, but its persistence as an unsolved question. Many unusual objects in astronomy eventually yield their secrets. What once looked strange often finds a home in a broader theory as more data comes in. But Hoag's object, decades after its discovery, still holds its mystery. Every new observation confirms its structure, sharpens its image, but does not erase the strangeness. Instead, it deepens the question. Why would a galaxy choose such a form? What processes could separate stars so neatly into a central sphere and an outer ring, with nothing in between? And perhaps the most unsettling thought is that there may be no single answer. It may not be the product of one event, but the intersection of several unlikely conditions, a rare collision, a precise angle, the right amounts of gas and dark matter, all coming together at just the right cosmic moment to create a shape that looks impossibly deliberate. If so, then Hoag's object is a reminder of how vast and varied the universe can be, how even the most careful classifications are still incomplete when faced with the creativity of nature. This difference, this refusal to fit, is why Hoag's object continues to fascinate. It is a galaxy unlike any other, not only in form but in its role as a challenge. It stands as a quiet question mark against the night sky, a symbol of how much we still don't know about the structures that fill the universe. And as astronomers point their instruments toward it again and again, they are not just studying a single galaxy. They are testing the boundaries of their own understanding, asking whether the rules we think we know are broad enough to hold the exceptions that nature so casually provides. When we speak of galaxies, we often focus on the grand structures themselves, the luminous spirals, the massive ellipticals, or the peculiar shapes carved by collisions. It's easy to forget that every discovery in the sky carries with it a human story. Behind each catalogue entry, each astronomical designation, there is usually a person, someone who spent long nights at the telescope, someone who trained their eyes on faint glass plates, someone who noticed a detail that others might have missed. In the case of Hoag's object, the name itself preserves the memory of one such observer, Arthur Allen Hoag. Arthur Hoag was born in 1921, and like many astronomers of his generation, he entered the field at a time when astronomy was transitioning from the patient art of visual observation to the more technological age of photography, spectroscopy, and radio detection. By the mid-20th century, the great observatories of the world were equipped with telescopes that had been improved over decades, and they were producing images of the cosmos with increasing clarity. Hoag himself was not primarily a galaxy specialist. His main work involved stellar classification and photometry, that is, the careful measurement of starlight. His career was built on the patient accumulation of data, the kind of work that rarely makes headlines, but that provides the foundation for broader theories. It was in 1950, while he was at the US Naval Observatory, that Hoag came across the unusual circular object that would one day bear his name. At the time, he was engaged in a survey project. The photographic plates captured wide fields of stars, and his job was to measure and classify them. These plates were, to a modern reader, astonishingly analog. They were literal pieces of glass coated with photographic emulsion, exposed over long hours under the starlight, and then developed in dark rooms. Each plate was precious. Errors could mean wasted nights, and conditions had to be ideal. Once developed, astronomers would examine them with magnifying lenses, combing through the details. That was where Hoag spotted it, a faint ring-shaped smudge unlike the others. His first instinct was cautious. Astronomers are trained not to leap to conclusions when they see something unusual. Many apparent oddities on photographic plates turn out to be defects, scratches, or artifacts of the emulsion. Hoag checked carefully to make sure the ring was not a flaw. It persisted. Then came the classification problem. If it wasn't an error, what was it? A planetary nebula? That was one possibility. A distant galaxy? That was another. The trouble was, it didn't look exactly like either. It looked like something in between, or perhaps something entirely different. Hoag described it in his notes with restraint. He didn't claim to have found a new class of galaxy. He didn't publish it with dramatic headlines. Instead, he placed it quietly in the record, a peculiar object worth further attention. It is this kind of modesty that often characterizes the best science. Hoag didn't overstate what he saw. He simply noticed, recorded, and allowed the evidence to speak for itself. In time, the community picked up on the oddity, and the galaxy that had once been just a faint circle on a plate began to draw more curiosity. The 1950s were a fertile period in astronomy. The field was expanding rapidly with the development of radio telescopes, which revealed an invisible universe of quasars and pulsars. Optical astronomy too was advancing, with larger telescopes at Palomar and other observatories pushing deeper into space. Amid these discoveries, Hoag's ring might have seemed like a small footnote. Yet, as decades passed and our ability to study galaxies improved, that footnote grew larger. It became one of those objects that refuses to be explained away, the kind that lingers in textbooks and lectures because it doesn't fit the tidy diagrams. For Hoag himself, the discovery was just one part of a long career. He went on to become the director of the Kitt Peak National Observatory in Arizona, one of the major centers of optical astronomy in the United States. Under his leadership in the 1970s, Kitt Peak expanded its research programs and played a key role in training new generations of astronomers. By then, Hoag's object had already been included in several catalogues as a peculiar ring galaxy, cementing his name in astronomy. It's interesting to think that while Hoag was managing an observatory filled with powerful instruments, his most famous legacy in popular science remained that curious moment of curiosity from 1950. It says something about the nature of discovery. Scientists can spend careers on detailed, technical contributions, but sometimes it is the quiet observation, the willingness to pause at the strange that endures. Hoag himself was never one to sensationalize the galaxy. He left the theories and the attempts at explanation to others, but his role was essential. Without his patient eye and his careful note-taking, this object might have been overlooked, perhaps even forgotten in the mass of countless faint galaxies. Instead, it now bears his name, ensuring that whenever students learn about this odd circular system, they also encounter the story of the man who first noticed it. When astronomers today read his 1950 paper, they find the description straightforward and almost understated. He simply pointed out that it did not resemble any known planetary nebula, nor did it quite resemble typical galaxies, and that further study was required. That was it. No grand theories, no sweeping claims, just curiosity in its purest form. It's almost refreshing in an age when discoveries are often announced with dramatic flair. Hoag's approach was measured, careful, and precise. One can imagine him in that moment of recognition, examining the plate, leaning closer under a magnifying lens, seeing the faint halo and the darker space around it. Did he feel excitement? Did he smile at the oddity? Or did he simply jot it down and move on to the next star? We can't know. But what we do know is that he left enough of a record for others to return to, and that is the essence of scientific work, leaving behind a trail that others can follow. As time went on, the object gathered more attention. Astronomers gave it the formal catalogue designation, PGC 45559, but among themselves and in public, it was almost always called Hoag's object. That naming is more than a formality. It anchors the galaxy in human history, attaching a face and a name to a puzzle. Every time someone speaks of Hoag's object, they are indirectly acknowledging the man who first saw it and thought it was worth remembering. There's something almost poetic about that connection, though of course we are avoiding poetry here. A galaxy 600 million light-years away, vast beyond comprehension, somehow tied by name to a single human being on Earth who happened to notice it on a glass plate. The universe is indifferent to names, but humans are not. For us, names provide continuity, memory, and a way of recognizing the people who carry curiosity forward. Hoag may not have set out to achieve fame in this way, but his name is now inseparable from one of the strangest galactic forms we know. Even today, when astronomers present images of Hoag's object, they often include a brief story about Arthur Hoag. It's not necessary for the science, but it adds a human thread. Students learning about galaxies are more likely to remember an odd ring if they also know that it was discovered in 1950 by a man working quietly at the Naval Observatory. The memory of the person enriches the memory of the object. It's also worth reflecting on how different the tools of 1950 were from those we use now. Hoag didn't have access to Hubble, or the James Webb Space Telescope, or massive computer simulations. He had a telescope, glass plates, and his own eyes. And yet, with those tools, he captured something that still defies explanation even in our advanced era. That contrast is humbling. It shows that while technology extends our reach, discovery ultimately begins with attention. The cosmos offers endless sights, but only if someone is looking carefully enough to see them. Arthur Hoag passed away in 1999, long before the highest resolution images of his galaxy were taken. He never saw the detailed Hubble photographs that so many of us have marvelled at since. But he didn't need to. His role was never to provide the final image or the final word. His role was to open the door. He gave the galaxy a place in the record, and others carried the work forward. That's how science builds itself, one observer at a time, each leaving a trace for the next generation. So when we speak of Hoag's object as a galaxy unlike any other, we're also speaking of Arthur Hoag's quiet contribution to the collective curiosity of humanity. He was the man who paused, who noticed, who wondered, and who gave us a mystery to carry into the future. When astronomers first encountered ring galaxies, long before Hoag's peculiar circle drew the spotlight, they already knew that the universe liked to experiment with form. Most galaxies, of course, are spirals or ellipticals, but every now and then telescopes reveal rings, loops, or arcs that seem to have been carved by invisible hands. At first glance, these might look like siblings to Hoag's object, but as with many families, appearances can be deceiving. Ring galaxies are usually creatures of violence. They are born from encounters, collisions, or near misses between galaxies. Picture one galaxy plunging through another, not like billiard balls colliding head-on, but more like stones dropped into a pond. The smaller intruder passes through the larger galaxy, disturbing its disk of gas and stars. This disturbance sends ripples outward, compressing gas and sparking waves of star formation that spread like shock fronts. Over millions of years, those ripples evolve into rings, glowing circles of new stars expanding away from the core. One of the best-known examples is the Cartwheel Galaxy, a spectacular system located about 500 million light-years away in the constellation Sculptor. Its structure is dramatic, a bright ring lit with star-forming regions, a smaller core at the centre, and faint spokes connecting the two like the remnants of the collision that created it. Astronomers studying the Cartwheel can trace its history. They see the signature of the impact, the evidence of interaction, the scars left behind by the galactic intruder. Even if you know nothing about astrophysics, the Cartwheel looks unsettled, almost explosive, its symmetry imperfect, its beauty forged in chaos. This is typical of ring galaxies. Their rings are rarely smooth. They may be warped, broken, or asymmetric. The central regions often show clear signs of disturbance, as though the galaxy has been jolted out of balance, and nearby there is usually a suspect, another galaxy in close proximity, sometimes visibly linked by tidal streams of stars or gas. In other words, the crime scene is rarely clean. Astronomers can follow the clues and reconstruct what happened. That's why Hoag's object stands apart. When you compare it to galaxies like the Cartwheel or other collision-born rings, the differences are glaring. Hoag's object shows none of the messy aftermath. Its ring is almost unnervingly smooth. Its core is perfectly round, undisturbed, and shows no hint of the chaos that a violent collision should have left behind, and crucially it sits in relative isolation. There is no obvious intruder nearby, no companion galaxy tugging at its structure, no visible bridge of material to suggest an encounter. If it was born from the same kind of collision that explains most ring galaxies, then the evidence has been erased far too neatly. Astronomers have puzzled over this for decades. One possibility is that the collision happened so long ago that all the debris has settled, leaving only the ring as a lingering echo. That might explain the smoothness. But then why is the core still so undisturbed? In most collisional rings, the central region bears the brunt of the impact, often looking distorted or misshapen. Hoag's object, by contrast, is almost serene. It looks less like a galaxy that has survived a cataclysm, and more like one that was designed, from the start, to be a circle. Another way to look at ring galaxies is through the lens of resonance. In some disk galaxies, gravitational interactions can set up resonant patterns that redistribute gas into ring-like structures. These are often tied to bars, elongated central features where stars and gas are funneled inward or outward. Barred spiral galaxies sometimes have rings surrounding their bars, but Hoag's object lacks a bar. It doesn't show the structural features that would make resonance a satisfying explanation. Once again, it seems to dodge the category. The contrast becomes clearer when you examine the populations of stars. In typical collisional rings, the stars in the ring are young, hot, and bright, the result of recent star formation triggered by the shock wave of the encounter. In the core, you often find older stars, sometimes mixed with younger ones, depending on how much gas was stirred up by the collision. Hoag's object does match part of this pattern. Its ring is full of young blue stars while the core is dominated by older, redder ones. But the separation between the two is far too sharp. There is that conspicuous gap, a zone where almost no stars exist. In collisional rings, you expect more overlap, more gradual blending. Hoag's object is like a galaxy that has drawn a line and declared, young stars here, old stars there, nothing in between. The mystery deepens when you think about how stable the ring appears. In collisional systems, the rings expand outward over time. They don't last forever. Eventually the stars disperse, the gas thins out, and the galaxy evolves into a more ordinary shape. But Hoag's object doesn't look temporary. Its ring is intact, its symmetry preserved. If it is an expanding wave, it has held its form for far longer than expected. That stability doesn't match the usual lifespan of collisional rings, which are fleeting episodes in galactic evolution. When the Hubble Space Telescope captured its famous image of Hoag's object, astronomers were struck by just how unlike other ring galaxies it appeared. The comparison to the Cartwheel and others made it even more obvious. While most rings bear the marks of chaos, Hoag's object seemed untouched, almost idealized. One astronomer remarked that if you asked a child to draw a galaxy with a ring, they might sketch something like this: simple, clean, perfect. But nature rarely works with such simplicity, especially on scales of hundreds of thousands of light years. This is why Hoag's object continues to attract attention, even among experts who have seen countless galaxies. It's not just that it looks different, it's that it refuses to follow the rules we know. If collisional dynamics can't explain it, and resonances can't explain it, then what does? Some have speculated about more exotic possibilities. Could it have formed through a slow accretion of gas that settled into a ring, while the central core remained untouched? Could it be the remnant of a galaxy that once had spiral arms, which somehow dissolved into a ring instead of collapsing into a disk? Each idea stretches our current models. None fits comfortably. To understand how unusual this is, you have to appreciate how robust galactic classification usually is. Even peculiar galaxies can often be explained by known processes. Collisions produce tidal tails, rings and warps. Resonances produce bars and rings. Mergers produce ellipticals. The categories may be broad, but they cover most cases. Hoag's object sits outside, a stubborn exception. And in science, exceptions are powerful. They remind us that our models are approximations, not complete truths. The universe doesn't read our textbooks. Of course, Hoag's object is not entirely alone. A few other galaxies with ring-like structures have been identified that share some of its features, but even among them, it stands out for its symmetry and isolation. It is often treated as the archetype of its own tiny category, a category of one, or at most a handful. That makes it both fascinating and frustrating. With so few examples, it's hard to build a theory. You can't run statistics on one galaxy. You can only compare, hypothesize, and wait for new observations. The contrast with ordinary ring galaxies is therefore crucial. Without those other examples, we might not even recognize how strange Hoag's object is. It would simply be one more curiosity in the sky. But when you set it side by side with the cartwheel, or with barred spiral rings, the differences leap out. The others tell stories of collisions, chaos, and transient forms. Hoag's object tells a story we can't yet read. It is a reminder that even in a universe where patterns dominate, there is still room for surprises. And that is what keeps astronomers returning to it. Not just the beauty of the image, though it is undeniably striking, but the sense that it is pointing to something unfinished in our understanding. Every time we compare it to normal ring galaxies, the gap grows wider, the anomaly sharper. It is not enough to say that Hoag's object is rare. We want to know why, and until we do, it will remain a galaxy that quietly breaks the rules. When you first see a clear image of Hoag's object, the symmetry almost makes you pause. It doesn't just look unusual, it looks deliberate. A golden core sitting right in the middle, a perfect dark gap surrounding it, and then a brilliant ring of stars forming a circle so precise it could be mistaken for something artificial. The human brain is wired to notice patterns, to find shapes and order in the world. We see faces in clouds, animals in constellations, order in randomness. But Hoag's object takes this to another level. It's not a case of us projecting patterns onto chaos. It really is almost geometrically perfect, and that is what makes it so uncanny. In astronomy, perfection is practically non-existent. Galaxies are messy. Spirals may be beautiful, but their arms are rarely even. They clump, they warp, they stretch unevenly. One side may be thicker than the other, pulled slightly by a neighbour or distorted by past encounters. Ellipticals, too, are not flawless spheres. They're often lopsided, flattened, or elongated. Even planetary nebulae, those glowing shells of gas surrounding dying stars, which can sometimes look circular in small telescopes, are rarely perfect circles when viewed in detail. The universe thrives on imperfection. Gravity pulls unevenly, gas clouds collapse irregularly, collisions leave behind scars. That's why Hoag's object unsettles astronomers. Its symmetry shouldn't exist on this scale. The ring is not just roughly circular, it's startlingly round, with hardly any variation in thickness. The core is placed almost exactly in the centre. The gap between core and ring is consistent all the way around, like the uniform space in a carefully designed piece of architecture. It looks manufactured, even though every instinct in science insists it isn't. Why is symmetry so rare? It comes down to the forces at play. Galaxies are vast, containing billions of stars, clouds of gas and dust, and invisible halos of dark matter. All of these components move, interact and evolve over billions of years. A single gravitational tug from a passing galaxy can warp a spiral arm. A burst of star formation can send gas clouds billowing unevenly. Even internal processes, like the dynamics of rotating stars and dark matter, tend to produce irregularities. On scales of tens or hundreds of thousands of light years, maintaining perfection is almost impossible. Yet here is Hoag's object, calmly defying that expectation. Astronomers often compare it to other ring galaxies to emphasize the strangeness. Take the Cartwheel Galaxy, for example. It has a ring, but the ring is jagged, filled with clumps and spokes, its symmetry broken by the violent collision that created it. Other ring galaxies show distortions, overlaps, or evidence of tidal forces at work. Hoag's object shows none of that. Its ring is smooth, unbroken, and evenly bright. It lacks the signs of chaos that should accompany such a formation. The symmetry raises practical questions. How did it form without leaving scars? If a collision created the ring, why is the central core untouched and perfectly spherical? If resonance or internal dynamics created it, why is the ring so clean, with no fragments or distortions? Even the dark gap between the core and ring is strange. In most galaxies, stars are scattered throughout, even if they are sparse in some regions. In Hoag's object, the void is so clear that it looks as though something actively swept it clean. This perfection problem has led some astronomers to joke that Hoag's object looks almost too good to be true. If someone fabricated a galaxy for a science fiction illustration, they might design it exactly this way: neat, centered, and pristine. But the universe, as we know it, does not usually produce such neatness, which is why the symmetry feels almost alien. Theories have been proposed to explain how such balance might emerge naturally. One idea is that the ring is the result of a very ancient collision, one that happened so long ago that all the irregularities have since smoothed out. Over billions of years, the clumps could disperse, leaving behind only the clean ring. But this raises another problem. If that much time has passed, why is the ring still filled with bright young blue stars? Those stars burn out quickly, often within a few million years. For the ring to glow as it does, star formation must still be occurring there. That suggests the ring is not ancient but active, complicating the timeline. Another idea is that the ring formed from accretion, gas falling onto the galaxy from outside, perhaps funneled by the surrounding dark matter halo. If this gas settled into a circular orbit, it could form stars in a ring-like structure. That might explain the ongoing star formation. But why would the gas arrange itself so evenly rather than forming clumps or spiral arms? And why would it leave such a sharp gap around the core? The questions pile up faster than the answers. This is why symmetry fascinates astronomers. In everyday life, we might take circles and straight lines for granted. We draw them easily, build them into our architecture, and use them as symbols of order. But in the natural universe, symmetry on large scales is a rarity. Planets are roughly spherical, yes, but even they bulge at the equator or bear the scars of craters. Stars form spheres under gravity, but they pulse, spin, and flare unevenly. On galactic scales, symmetry is almost unheard of, so when we see it, it demands explanation. It also speaks to something deeper in human psychology. We are drawn to symmetry because we associate it with design, stability, and beauty. In art, symmetry is often used to suggest harmony. In nature, it often signals health or fitness. Symmetrical faces, balanced leaves, patterned shells. So when we look at Hoag's object, our brains can't help but react with awe. It presses the same buttons as a perfectly round pearl or a flawlessly cut gem, except on a scale of hundreds of thousands of light years. It is beauty written in starlight. But science doesn't stop at beauty. It asks why. And in this case, the why remains elusive. Every explanation leaves something unaccounted for. If it's a collision, where are the scars? If it's resonance, where is the bar? If it's accretion, why is the ring so clean? If it's some other process, why don't we see more galaxies like it? The symmetry problem is not just aesthetic, it's scientific. It tells us that our models of galaxy formation may be missing something, some pathway that allows such near-perfect forms to exist. Astronomers sometimes imagine what Hoag's object would look like if you lived inside it. From the core, the view would be astonishing. Look outward in any direction, and after a stretch of darkness, you would see a brilliant ring of stars encircling the sky, a halo shining around the edges of your universe. From the ring, the view inward would be equally strange. The golden core would glow at the centre, perfectly framed, like a lantern suspended in the middle of the cosmos. That inner perspective only reinforces how uncanny the symmetry is. It's not just a trick of perspective from Earth. From any angle, this galaxy is a circle around a sphere, a shape that seems designed for attention. And yet, despite all of this, it is natural. No hand drew it, no design was imposed. It is, as far as we know, the product of physics, gravity, and time. That is perhaps the most unsettling part of all. The universe, without intention, has produced something that looks intentional. In that sense, Hoag's object is a reminder of how little we truly control about our search for order. We categorize, we model, we expect messiness, and then the cosmos offers us perfection, daring us to explain it. The perfection problem isn't solved yet. Astronomers continue to gather data, running simulations to see if such a structure can emerge naturally. Some models suggest it might be possible, under just the right conditions, for gas to form into a stable ring while leaving the core untouched. Others argue that we simply haven't observed enough galaxies to know how rare this really is. Perhaps there are more Hoag-like systems waiting to be found, hidden among the billions. If so, each one could help reveal whether this symmetry is a freak accident or a missing chapter in galactic evolution. For now, though, Hoag's object remains unique in its perfection. A galaxy that should not look the way it does, and yet stubbornly does. A reminder that the universe is under no obligation to match our expectations. And perhaps that is why its symmetry feels uncanny, because it forces us to see that perfection, in nature, is the exception, not the rule. And when it appears, it leaves us wondering what we've missed. At the heart of Hoag's object lies something that at first glance might seem almost ordinary. It is a compact sphere of stars, glowing with a warm golden hue. In photographs, this core appears calm, smooth, and round, without the jagged features or spiral arms that so many galaxies display. It is easy to mistake it for something simple, perhaps just another elliptical galaxy, unremarkable on its own. Yet in the context of Hoag's object, this golden centre is one of the strangest pieces of the puzzle. Because here, at the middle of a galaxy that breaks the rules, the core is too normal, too untouched, too serene. The colour alone tells part of the story. Stars come in many shades, from hot blue giants that blaze fiercely and die young, to cooler yellow stars like our sun, to dim red dwarfs that can burn steadily for trillions of years. The overall colour of a stellar population acts as a kind of clock. A galaxy glowing with blue light is usually filled with young, massive stars. Their brilliance dominates, but their lifespans are short, so they mark regions of ongoing star formation. A galaxy that leans golden or reddish, on the other hand, is usually older. Its massive stars have already lived and died, leaving behind longer-lived stars that shine more softly. Hoag's object's core glows gold, which suggests it is made of stars that are no longer in the first flush of youth. They are stable, settled, perhaps billions of years old. That in itself is not unusual. Many galaxies have cores of older stars, but the way this core sits, so perfectly round, so sharply divided from the surrounding ring, makes it peculiar. In most galaxies, the central bulge is connected smoothly to the rest of the system. Spiral arms stretch outward, or disks spread around them. Even in ellipticals, there is no sharp cut-off, no sudden emptiness between the core and outer regions. Hoag's object is different. The core is like an island floating in a sea of black, with no bridge connecting it to the stars of the ring. When astronomers look at this golden hub, they ask what history it reveals. Was this the original galaxy? A small elliptical that once stood alone, later surrounded by the younger ring? If so, how did the ring form without disturbing the core? Did the core once belong to a spiral, stripped of its arms, leaving only the central bulge intact? Or is it the remnant of some merger long ago, smoothed into a ball while the outer regions reorganized into a circle? Each possibility raises more questions than it answers. The smoothness of the core is another striking feature. Many galactic centers are dynamic places bustling with activity. Bars of stars may cut across them, channels of gas may stream inward, and supermassive black holes may dominate their innermost regions. In high-resolution images, these cores often look grainy or clumpy, textured with dust lanes and star clusters. But Hoag's core looks calm. It is nearly spherical, with no obvious distortions. It gives the impression of something undisturbed for a long time, untouched by the chaos that usually accompanies galactic evolution. And yet, we know that no galaxy is ever truly untouched. The universe is a crowded place. Galaxies tug on one another, and internal dynamics shift populations of stars. To achieve such a smooth and isolated core, Hoag's object must have gone through a unique history. Some astronomers suggest that the core may have once been an elliptical galaxy in its own right, long before the ring formed. If that is true, then Hoag's object is essentially a galaxy wrapped in another galaxy, two structures coexisting in one. The gap surrounding the core only amplifies the mystery. It's not just that there is a ring, it's that the core is separated from it by emptiness. Normally stars are scattered throughout galaxies in continuous distributions. Even if density drops, you still find stragglers, clusters, or gas clouds filling the space. In Hoag's object, the space between the core and the ring looks eerily clean, as though something actively swept it out. Did gravitational resonances clear the area, pushing material outward into the ring? Did some past event expel the stars, leaving behind a void? The absence of material there makes the core look even more isolated, as though it doesn't belong to the ring at all. Peering into this central sphere, astronomers also wonder about the role of the supermassive black hole that likely sits at its center. Nearly all galaxies are believed to harbour black holes at their cores, often millions or even billions of times the mass of the Sun. These black holes shape their galaxies in subtle but powerful ways, regulating star formation through jets and radiation. Could Hoag's black hole have influenced the formation of the ring? Could it have consumed or expelled gas from the central regions, preventing stars from forming close by while allowing them to ignite farther out? These possibilities are considered, but none yet provide a complete picture. From Earth, the golden colour of the core gives it a comforting warmth. In contrast to the cool blue light of the ring, it feels steady, settled, ancient. You could almost think of it as the elder of the galaxy, surrounded by a youthful generation shining brightly at the edges. That contrast of ages, right next to one another but separated by a void, is part of what makes Hoag's object so compelling. It is like two galaxies locked together, one old, one young, neither touching the other. And still, the core itself holds secrets. How many stars does it contain? Billions, certainly, though estimates vary depending on how we interpret its brightness. Are there globular clusters orbiting it, like those that swarm around the Milky Way's bulge? What about its black hole? Is it active, feeding on gas, or quiet, waiting in silence? The golden glow we see from Earth is an average, the combined light of countless stars blended into one smooth sphere. But within that glow are individual stories, individual stars with their own planets, their own histories, their own lifespans. The core is not a single object, but a crowded city of suns, each one too faint and too far for us to separate, yet together creating the impression of calm. Astronomers who model galaxies try to simulate how such a core might persist in such isolation. Some suggest that the core may have once been part of a spiral galaxy, its arms stripped away by a past encounter, leaving only the central bulge. Others suggest it could be the remnant of a merger between smaller galaxies, smoothed into a sphere by gravitational relaxation. But in either case, the question remains: how did the ring form without disturbing the core, and why is the separation so sharp? For observers on Earth, the golden hub serves as an anchor in the photographs. Without it, the ring might look like just another arc or circle of stars. With the core in place, perfectly centered, the whole structure becomes uncanny. The eye is drawn first to the core, then to the empty space, then to the ring beyond. It feels designed, like a diagram of celestial geometry. The calm center only heightens the impression that the galaxy was arranged with purpose, and yet, as astronomers remind themselves, it is only physics at work. The core is simply the product of billions of years of star formation and stellar aging. Stars formed long ago, consumed their fuel, and now shine steadily in the twilight of their lives. There is no intention, no design, only the quiet outcome of gravity, gas, and time. Still, the mind resists. The symmetry of the core and ring combination feels intentional, even though it is not. The golden center is therefore more than just a cluster of stars. It is the heart of the mystery. Without it, Hoag's object might be dismissed as just another unusual ring galaxy. With it, the galaxy becomes a puzzle that refuses to fit the categories. The serene sphere in the middle is what makes the ring so strange, what makes the void so sharp, what makes the symmetry so uncanny. It is the eye at the center of the cosmic bullseye, a reminder that even in a universe full of chaos, there can be order so precise it unsettles us. If the golden core of Hoag's object seems ancient and settled, the ring surrounding it feels like the opposite, vibrant, restless, and young. It is a halo of blue light, glowing with the energy of hot, massive stars that have only recently been born. Against the quiet warmth of the center, this ring looks electric, almost alive, like a band of neon wrapped around the galaxy. The contrast is startling. One part of the galaxy speaks of old age and stability, while the other is bursting with youth, crowded with stars that will live fast and die spectacularly. The colour tells us much of the story. In astronomy, blue stars are the sprinters of the stellar world. They are large, often many times the mass of the Sun, and because they are so massive, they burn through their nuclear fuel at an incredible pace. Some of them may shine for only a few million years before exhausting themselves and ending in supernova explosions. Compare that to stars like the Sun, which can last 10 billion years, or red dwarfs, which can persist for trillions. Blue stars are brief, but while they exist, they dominate the light of their regions. That is why the outer ring of Hoag's object glows so strongly in blue. It is filled with these short-lived giants, outshining any smaller, longer-lived stars that might also be forming there. This tells astronomers that the ring is not ancient. If it were billions of years old without ongoing star formation, the blue stars would have already burned out, leaving behind only the dimmer, redder stars. The fact that we see it glowing so brightly now means that star formation must be happening continuously in the ring. Gas is still available there, collapsing into clusters, igniting new generations of stars, replenishing the population of brilliant blue giants. The ring is therefore not just a structure, but a nursery, a belt of stellar birth wrapped around the galaxy. But why the ring? Why is star formation concentrated there and not throughout the galaxy? That is one of the great questions that makes Hoag's object so unusual. In most galaxies, star formation occurs in sprawling regions spread across spiral arms, or in pockets scattered through irregular shapes. In Hoag's object, it is confined, almost imprisoned, within this circular band. The emptiness between the ring and the core makes this even more striking. It is as if the galaxy has drawn a boundary line declaring that stars will be born here, and only here. For astronomers, this confinement raises fascinating possibilities. Perhaps gas was somehow funneled outward to this distance, piling up in a ring where conditions were right for collapse. Perhaps a long ago event pushed material outward, leaving a wave of star formation in its wake, or perhaps the gravitational field of the galaxy, influenced by its dark matter halo, shepherds gas into orbits that naturally form a ring rather than filling the whole disk. Whatever the mechanism, it has created a band of light that defies the usual messy sprawl of galaxies. Looking closely at the ring, astronomers can see that it is not perfectly uniform. Even within its remarkable symmetry, there are brighter knots, clumps where star formation is especially intense. These are likely regions where massive clusters of stars are forming, places where gases collapse more efficiently. In those knots, dozens or hundreds of hot stars might be burning side by side, destined to explode in supernovae that will send shockwaves rippling through the ring. Each explosion will briefly outshine the rest of the galaxy, adding drama to the otherwise serene circle. It is strange to imagine this. From our distant vantage point, the ring looks calm, even delicate, a smooth blue halo, but up close, it would be anything but calm. It would be a storm of ultraviolet radiation, stellar winds, and supernova blasts, a chaotic environment where new stars are constantly forming and old ones are dying in violent outbursts. To live near the edge of that ring would be to inhabit a neighbourhood in perpetual turmoil, bathed in the energy of giants. And yet, the ring holds. Despite the chaos within, its overall shape is smooth, its outline unbroken. That stability combined with its youth is what makes it so difficult to explain. Usually active star-forming regions are messy. Gas clouds collapse unevenly. Clusters form in irregular patches. Turbulence stirs the medium. Hoag's ring, however, is organised. It gives the impression of structure imposed on chaos, a circle drawn where you would expect disorder. The size of the ring adds to the wonder. At roughly 120,000 light-years across, it is larger than the Milky Way. Imagine billions of stars spread along that circumference, each adding its light to the whole. The scale is beyond comprehension. If you tried to travel from one side of the ring to the other at the speed of light, it would take longer than the entire recorded history of humanity. And yet, to our eyes, it looks like a single clean band. Astronomers studying the ring have tried to model its dynamics. Some simulations suggest that rings can persist if gas flows are carefully balanced, replenishing material at just the right rate to sustain star formation while keeping the structure intact. Others suggest that such rings should disperse quickly, making Hoag's object a fleeting snapshot of a rare phase. If that is the case, then our view of it is even more extraordinary. It would mean we are witnessing the galaxy at a moment that will not last long, at least not in cosmic terms. Millions of years from now, a blink to the universe, though far longer than human timescales. The ring may fade, the blue stars may die, and the structure may dissolve into something more ordinary. For now, though, it shines. Its blueness marks it as young, but its symmetry makes it look timeless. It is both a momentary phase and a lasting image, frozen in our telescopes. Every photon of blue light we see from it tonight left those stars 600 million years ago, long before humans existed, long before Earth's continents had taken their modern form. When the dinosaurs still roamed the planet, the light that now enters our eyes was already halfway through its journey. The blue glow is both ancient and young at once, ancient in its travel, young in its meaning. The ring also raises questions about the galaxy's future. If star formation continues at this pace, how long will the gas supply last? Will the ring eventually exhaust itself, leaving behind only older stars that fade to red? Will the core and the ring ever merge, filling the empty gap with new populations of stars? Or will the galaxy remain split, its inner and outer regions living separate lives forever? These are questions astronomers cannot yet answer. All they can do is keep observing, keep comparing, and keep wondering. For those of us simply gazing at its image, the ring offers something else: beauty. The contrast between the golden heart and the blue halo is one of the most striking sights in astronomy. It is a reminder that the universe, in its endless complexity, sometimes creates forms that appeal not only to our scientific curiosity, but also to our aesthetic sense. Hoag's object is not just a problem to solve, it is an image to marvel at, a sight that can quiet the mind and stir the imagination. The halo of blue filled with hot, short-lived stars is a symbol of impermanence. Those stars will not last long. They will burn out, explode, and scatter their material back into the galaxy. Yet in doing so, they will seed the next generations of stars, recycling their elements into new suns and perhaps even new planets. The ring is therefore not just a circle of light, but a circle of renewal. It is a cosmic reminder that even in the most mysterious forms, the cycle of birth and death continues. When people first look at an image of Hoag's object, their eyes usually travel from the bright golden centre outward to the brilliant blue ring. It's only after that first moment of awe that something else becomes clear. Between those two glowing structures, there is nothing. A dark, empty band of space, wide enough to fit entire galaxies, yet seemingly devoid of stars. It is that gap that turns Hoag's object from unusual to uncanny. Because in most galaxies, emptiness like this does not exist. Galaxies are usually full of stars. Even in regions that appear dim, there are countless suns scattered faintly across the darkness. Spiral galaxies fill the space between their cores and arms with a disk of stars, dust and gas. Ellipticals spread their light smoothly, fading gradually but rarely leaving clear boundaries. Even irregular galaxies, chaotic in form, scatter stars haphazardly throughout their volume. In all these cases there is continuity. Light fades but does not disappear. In Hoag's object, however, the gap is clean. It looks as though someone has carved out a moat around the core, sweeping the stars away before lighting the ring around the edges. Why is this so strange? Because gaps are unstable. If stars are orbiting under gravity, they should fill space in gradual distributions. Gas clouds, too, should spread, forming stars at multiple radii. For a wide region to remain empty, something must have actively cleared it, or prevented stars from forming there in the first place. That is why astronomers find the gap so unsettling. It is not simply an absence, it is an absence that demands explanation. One idea is that the gap was carved out by a collision long ago. If another galaxy plunged through the centre, it could have sent a shock wave rippling outward, pushing gas into the ring while leaving the middle relatively empty. In this picture, the gap is the aftermath of that wave. Gas was swept out and stars formed only where the material settled, leaving behind the clean space around the core. This is similar to how other ring galaxies form, but in those cases the gap is rarely so pristine. Debris usually lingers, and stars continue to fill in. In Hoag's object, the emptiness is sharper, more deliberate. Another possibility is that resonances within the galaxy's gravitational field cleared the space. Just as orbital resonances in planetary systems can carve gaps in asteroid belts or rings of dust, gravitational patterns within galaxies can sometimes redistribute material. If a resonance pushed gas outward to a stable orbit, it might leave the middle depleted. That could explain why the ring formed at a particular distance, leaving the core isolated. But resonances usually leave behind partial structures, arcs or bars, not entire empty zones as wide and uniform as this. Some astronomers suggest that feedback from the galaxy's central black hole could have played a role. Nearly every galaxy harbours a supermassive black hole in its centre, and these giants can influence their surroundings dramatically. When they feed on gas, they can release enormous amounts of energy, blasting material outward in winds and jets. Perhaps Hoag's black hole expelled gas from the inner regions, preventing star formation there and forcing it to happen only farther out in the ring. This would fit with the idea that the golden core is old and quiet, while the outer ring is still active. But again, the precision of the gap is hard to explain. Black hole feedback tends to be chaotic, producing bubbles and outflows, not perfect circles. The gap becomes even more intriguing when you consider its size. It is not a thin band, but a vast region spanning tens of thousands of light years. That's enough room for countless stars and clusters, Yet in images of Hoag's object it appears almost entirely dark. In reality, there may be a faint population of stars there, too dim for us to see from our distance, but if they exist, they are sparse compared to the glowing populations in the core and ring. The contrast is striking, and it makes the emptiness feel real, even if not absolute. From a human perspective, the gap adds to the sense of design. The golden core, the dark band, the blue halo, it looks like a cosmic symbol, a layered target painted against the night. The absence of stars in the gap makes the shape stand out more clearly. Without the gap, the galaxy might look like an unusual spiral, or a distorted elliptical. With the gap, it becomes singular, unforgettable. It is not just the presence of the ring that matters, but the absence that frames it. Astronomers often compare this emptiness to the spaces we see in planetary systems. The rings of Saturn, for example, are divided by gaps carved by resonances with moons. The asteroid belt in our solar system shows gaps created by Jupiter's gravity. In both cases, orbits become unstable at certain distances, clearing the region of material. Could something similar be happening on a galactic scale in Hoag's object? Could resonances with the mass of the core or the distribution of dark matter carve the gap? If so, Hoag's object might be an enormous version of Saturn's rings, shaped by gravity into clear divisions. The analogy is tempting, but so far the physics doesn't match perfectly. The scale, the sharpness, and the persistence of the gap all remain puzzling. It is worth considering how the gap changes our emotional response to the galaxy. Without it, Hoag's object might still be beautiful, but it would not feel uncanny. The gap is what makes it look like a symbol, what makes it feel designed. The emptiness sharpens the edges of the core and ring, making them look more intentional, more like parts of a pattern. Our minds are drawn not only to what is present, but to what is missing, and in this case, the missing stars make the galaxy unforgettable. Peering into that darkness, one might wonder what it would be like to exist there. Imagine a planet orbiting a star within the gap, a rare survivor in the empty band. Look outward, and the sky would be unusual. On one side, the golden core would shine like a crowded city of stars, glowing softly. On the other, the blue ring would arc across the heavens, blazing with young suns. Between them would stretch blackness, dotted only with faint points. It would feel like living in the moat of a cosmic fortress, cut off from both the old heart and the young halo, suspended in a strange in-between. The gap also holds significance for the galaxy's future. Will it remain empty forever? Or will stars eventually drift in, filling the space and smoothing out the contrast? If the ring eventually disperses, will the gap collapse, leaving behind a more typical disk? Or will Hoag's object continue to preserve its structure, defying the usual course of galactic evolution? These are questions that require time, not years or centuries, but millions and billions of years. For now, we can only freeze the image, look at what it is, and speculate on what it might become. The strange band of emptiness around the core may be one of the keys to solving the mystery of Hoag's object. If we can explain how it formed and why it persists, we may be closer to understanding the entire galaxy. For now, though, it remains one of its most haunting features, a reminder that sometimes the most fascinating parts of the universe are not what we see, but what we don't. When you look out at the night sky and imagine galaxies, it's easy to think of them as finished works of art, like paintings hanging in the darkness, already complete. Spirals with their arms fully extended, ellipticals glowing in their smooth symmetry, irregulars scattered like splashes of paint. But in reality, galaxies are not finished at all. They are the result of billions of years of processes, and those processes are ongoing. To understand why Hoag's object is so unusual, it helps to remember how galaxies usually form and evolve, guided by the invisible hands of gravity. Gravity is the architect of galaxies. In the earliest universe, after the Big Bang, matter was spread out more evenly than it is today, but it was not perfectly even. tiny fluctuations in density, regions slightly heavier or lighter than their surroundings, began to grow under gravity's pull. Heavier regions attracted more matter, which made them heavier still, a cycle of collapse and concentration. Over millions of years, these regions grew into the first clumps of gas and dark matter, the seeds of galaxies. At first, these clumps were chaotic clouds of hydrogen and helium gas, threaded with dark matter that we cannot see but whose gravity we can measure. The gas began to cool and collapse, forming the first generations of stars. These early stars were often massive and short-lived, burning out quickly and exploding as supernovae. Those explosions seeded the surrounding gas with heavier elements, enriching the galaxy and setting the stage for future generations of stars and planets. As time went on, the galaxies grew by merging with one another. Small systems combined into larger ones, their stars mingling, their gas clouds colliding, their dark matter halos merging into bigger structures. This process is sometimes described as hierarchical assembly. Galaxies are built from the bottom up, starting small and growing larger through mergers and accretion. Collisions were not gentle. They distorted shapes, triggered starbursts, and sometimes destroyed delicate structures like spiral arms. Yet over time, galaxies settled into recognizable forms. Spirals are among the most familiar results of this process. They typically form when a galaxy has enough cool gas to create a rotating disk. Stars and gas settle into orderly orbits around the center, and spiral patterns emerge as density waves move through the disk, triggering star formation in arcs that look like arms. These spirals are dynamic, not static. Stars move in and out of the arms, gas clouds collapse, and new stars are born while old ones die. Yet the overall pattern persists, a graceful arrangement created by gravity's balance of rotation and collapse. Ellipticals are often the product of mergers. When two spirals collide, their ordered disks are disrupted, stars scatter into random orbits, gas clouds are consumed in bursts of star formation, and the end result is a smooth, featureless spheroid. Ellipticals tend to be older and redder, with little gas left for new stars. They are the quiet retirees of the galactic population, glowing steadily without the clamour of new births. Irregular galaxies, as their name suggests, are shaped by disruption. They may be small systems tugged at by larger neighbours, or remnants of past collisions that never settled into neat forms. They are reminders that not all galaxies fit the categories cleanly, though even their chaos has causes we can trace. In all of these cases, though, there are patterns. Spirals have continuous disks linking their cores and arms. Ellipticals are smooth throughout. Even rings, when they appear, are usually the result of collisions or resonances that leave behind telltale scars. The guiding force is always gravity, working with gas, dark matter, and time to shape galaxies into forms we can classify and understand. Hoag's object, when placed against this backdrop, refuses to cooperate. Its golden core looks like an elliptical, but its outer ring looks like the aftermath of a collision. The gap between them looks like something swept clean. But the whole structure is too clean, too symmetric, too stable. It does not resemble the products we expect from the usual dance of gravity. It is as though it learned the steps of the dance but performed them differently, skipping moves or inventing new ones that don't fit the usual choreography. Astronomers often use computer simulations to study how galaxies form under gravity. They input the laws of physics, the properties of dark matter, the cooling of gas, and let billions of virtual years play out. The simulations produce spirals, ellipticals, and irregulars with remarkable accuracy. They can even reproduce ring galaxies when they simulate collisions. But producing something that looks like Hoag's object, with its perfect symmetry, its isolated core, its pristine gap, and its luminous ring, remains difficult. The dance of gravity usually leaves footprints, but in Hoag's object the floor looks polished, the marks erased. To appreciate how rare this is, Imagine the chaos of real galactic encounters. When two galaxies pass near one another, gravity pulls out long tidal tails, streams of stars stretching into space. Disks warp and twist. Rings form, but they're often lopsided, clumpy and temporary. Over time, the galaxies merge, and the chaos settles into a new form. But Hoag's object looks like the chaos never happened. It looks like the end product of some process we don't yet understand, one that managed to create order without leaving scars. This is why astronomers return again and again to the question of its origin. Did gravity, acting alone, sculpt this shape through some rare combination of factors? Or is there some additional process at work, something in the physics of gas dynamics, star formation, or dark matter that we haven't yet accounted for? If it is gravity's dance, then the choreography is stranger than we thought. Even so, it's worth remembering that every galaxy, no matter how odd, is a testament to gravity's reach. Gravity is weak compared to other forces, but on cosmic scales, it dominates. It takes the raw ingredients of the universe and arranges them into forms that can last for billions of years. Without gravity's pull, the gas after the Big Bang would have remained a thin mist, never collapsing into stars, planets, or galaxies. Every spiral arm, every glowing bulge, every faint dwarf galaxy is a mark of gravity's long patience. Hoag's object may not fit the rules, but it is still a child of gravity, shaped by the same universal force that binds our own Milky Way together. When astronomers look across the universe, one of the most important lessons they've learned is that galaxies are not isolated sculptures sitting quietly in space. They are dancers in a crowded ballroom, constantly tugging at one another, colliding, merging, and reshaping themselves. In fact, collisions and mergers are not rare events at all. They are the rule. Over billions of years, nearly every galaxy has been touched, pulled, or transformed by a neighbour. This is the natural way of things, and it explains why so many galaxies look the way they do. But when we turn our gaze to Hoag's object, that rule seems to falter. If rings are usually the scars of cosmic encounters, then Hoag's perfect circle is a scar that looks more like a flawless design. Collisions between galaxies are nothing like collisions we imagine in everyday life. When two cars crash, metal bends and fragments scatter. When galaxies collide, their stars almost never smash directly into one another. Stars are so far apart that even in the most dramatic galactic crashes, the chances of two individual stars colliding are vanishingly small. Instead, what collides are the clouds of gas, the tidal fields of gravity, and the delicate structures that hold the galaxies together. Gravity stretches them. Gas clouds slam into one another, triggering bursts of star formation, and over time the galaxies merge into new shapes. Ring galaxies are often the children of these events. When a smaller galaxy plunges through the disk of a larger one, the encounter sets off a ripple, much like a stone dropped into water. That ripple compresses gas as it moves outward, and compressed gas collapses into new stars. The result is a ring of star formation expanding away from the centre. For a while, the galaxy wears this ring like a crown, glowing with the blue light of newborn stars. Eventually, though, the ring disperses, the starburst fades, and the galaxy settles into a different form. The ring is temporary, a snapshot in a long history of chaos. One of the best examples of this process is the Cartwheel Galaxy. Its appearance is dramatic. A central hub, a ring of bright blue stars and faint spokes connecting the two, like the remnants of a wheel after an impact. Astronomers studying the Cartwheel have been able to trace its history. A smaller galaxy passed through it, disturbing its structure and setting off the starburst that created the ring. It is a textbook example of how rings form from collisions. The Cartwheel looks dramatic, but it also looks messy. There are asymmetries, irregular clumps, and lingering distortions that tell the story of the violence it endured. And this is where Hoag's object defies expectation. If it too was born from a collision, then it should carry the same signs. distortions in the core, irregularities in the ring, remnants of the intruder galaxy nearby, but none of those signs are present. The core is smooth and spherical, showing no evidence of being disturbed. The ring is nearly perfect, with symmetry far beyond what we see in other collisional systems, and the intruder, if there was one, is nowhere to be found. There is no obvious neighbour nearby, no tidal streams or bridges linking Hoag's object to another galaxy. It hangs in isolation, as though it formed its structure without the help of external violence. This absence of evidence makes astronomers uneasy. On one hand, collisions explain so much about galaxies that to dismiss them here feels reckless. On the other hand, insisting on a collisional origin requires stretching the explanation until it no longer fits comfortably. Perhaps the collision happened billions of years ago, so long ago that all the debris has dispersed and all the scars have healed. That could explain the smoothness. But if that were true, how is the ring still filled with young blue stars? Those stars don't last billions of years. The ring would need to keep forming new ones, which means the process that sustains it is ongoing, not ancient. That contradiction leaves the collision model unsatisfying. Mergers too struggle to explain Hoag's object. When galaxies merge, the result is usually an elliptical. Spirals lose their arms, stars scatter into random orbits, and the system relaxes into a featureless glow. Mergers are messy, and while they can leave behind tidal tails and rings in the short term, those features fade as the system settles. Hoag's object, with its crisp separation between core and ring, does not look like the remnant of a messy merger. It looks like something that skipped that chaos entirely. Some astronomers have proposed hybrid scenarios. Maybe Hoag's object started as an elliptical, and then gas accreted around it from outside, forming the ring. Or maybe a collision did happen, but in a way so precise and so unusual that it left behind none of the expected scars. These ideas acknowledge the role of encounters while trying to account for the differences, but they are speculative, and without more evidence they remain possibilities rather than conclusions. The difficulty here is not just about one galaxy, it is about the reliability of our models. If collisions and mergers explain most galaxies, then exceptions like Hoag's object test the boundaries of those explanations. They remind us that the universe can produce outcomes we did not predict. If our models can't account for them, then our understanding is incomplete. And science thrives on such incompleteness. Each exception is a doorway to deeper knowledge, a chance to refine our theories and see where they fall short. From another perspective, the absence of collisional scars in Hoag's object is almost comforting. It suggests that not every galaxy is doomed to disorder, that under some rare conditions gravity and gas can conspire to create harmony rather than chaos. It is as though the universe, usually content with messiness, decided in this case to try something elegant. Whether that elegance is the result of a forgotten collision, a rare balance of forces, or something else entirely, it leaves us with an image that feels more like art than accident. For the astronomers who study galactic dynamics, this raises a haunting question. If Hoag's object should not exist, then what else is out there that we have not yet seen? Is it truly unique, or are there other galaxies, hidden in the depths of space, that share its perfection? If there are, then collisions and mergers may not be the only pathways to rings. If there aren't, then Hoag's object is even more extraordinary, a singular outcome of cosmic history. Either way, it challenges our understanding of how galaxies grow, interact, and change. And so, as telescopes continue to survey the skies, astronomers keep their eyes open for more Hoag-like systems. Each new discovery could help decide whether collisions are enough to explain the galaxy, or whether something entirely new is required. Until then, Hoag's object remains a reminder that in a universe built on collisions, sometimes the scars don't look like scars at all. When astronomers describe Hoag's object, they often find themselves caught between two possibilities. Either it is the product of a highly improbable coincidence, the sort of chance event that could happen once in a billion galaxies, or it is the product of physical laws and processes that we don't yet fully grasp. Both options are unsettling in their own ways. A coincidence of this scale makes us question the odds, while hidden physics makes us question our understanding. In either case, the galaxy stands as a quiet challenge, daring us to decide which explanation feels less impossible. The coincidence argument is in some sense the simplest. The universe is vast, with hundreds of billions of galaxies in the observable portion alone. Even if rare events are extremely unlikely, the sheer number of galaxies means that unlikely things can still happen somewhere. Just as a shuffled deck of cards produces unique sequences every time, the cosmic shuffle of matter over billions of years can occasionally arrange itself into something surprising. Hoag's object could be one such arrangement, a galaxy that just happened to end up with its core and ring aligned so perfectly, its gap so clear, its symmetry so uncanny. In this view, it is not a new type of galaxy at all, but simply a 1 in a billion oddity. But coincidence alone can be unsatisfying. Science thrives on explanations, and to say that something just happened feels like surrender. Astronomers prefer to trace outcomes back to causes, to show how known forces and processes combine to create the forms we see. With Hoag's object, the coincidence explanation works only if no other mechanism is found. Until then, researchers are reluctant to stop asking why. That's where the possibility of hidden physics comes in. Perhaps the galaxy reveals something about the way matter behaves on large scales that we haven't yet accounted for. It might involve dark matter, the invisible mass that surrounds galaxies and dictates their dynamics. If Hoag's object has an unusual dark matter distribution, it could explain why gas settled into a ring instead of a disk, why the core remained untouched, and why the gap persists. Some models suggest that dark matter halos can produce resonances, guiding gas into circular orbits. If Hoag's halo has just the right shape or density, it might have sculpted the ring in a way that ordinary halos do not. Another possibility lies in the physics of gas flows. Galaxies grow not only by colliding with one another, but also by drawing in fresh gas from intergalactic space. This gas, funneled along cosmic filaments of the large-scale structure, can fall into a galaxy and form new stars. If the gas fell into Hoag's object in just the right way, perhaps it could have formed a ring rather than filling the whole system. That would make the galaxy not coincidence, but a clue to how gas accretion works under rare conditions. Then there is the role of feedback. As stars form, they influence their surroundings through radiation, winds, and supernova explosions. These processes can sweep gas into new configurations, creating cavities, shells, or rings. In Hoag's object, feedback might have cleared the inner regions while triggering star formation in the outer ring. But to produce such a perfect circle, the feedback would need to be incredibly uniform, and uniformity is rarely nature's style. Each of these possibilities pushes at the edges of current models. None are entirely satisfying, but none can be ruled out. This is why Hoag's object sits in the liminal space between coincidence and hidden physics. It could be one or the other, or perhaps both. Maybe a rare coincidence of timing and geometry occurred, but hidden physics made it possible. Maybe the galaxy's dark matter halo has an unusual shape, and a chance flow of gas happened to line up with it. The result would look improbable, but the underlying cause would be physical rather than miraculous. What makes this question so compelling is that it reflects a larger theme in science. How do we decide when something is coincidence and when it is law? If you flip a coin 100 times and get heads 90 times, you might suspect a hidden bias in the coin. If you flip a coin 1 billion times and once get 90 heads in a row, you might chalk it up to chance. With galaxies, the scale is even larger and the stakes are higher. Hoag's object could be the equivalent of 90 heads in a row. Improbable, but not impossible. Or it could be the equivalent of a biased coin, a sign that our physics is incomplete. Astronomers approach this problem by searching for more examples. If Hoag's object is truly unique, then coincidence becomes more likely. If we find others like it, then hidden physics becomes harder to ignore. So far, only a few vaguely similar galaxies have been spotted, none quite as perfect, but enough to raise suspicion. Perhaps Hoag's object is not entirely alone. Perhaps it is the first known example of a small population we have only begun to notice. This search is aided by modern sky surveys, which scan enormous swathes of the sky with digital cameras. Projects like the Sloan Digital Sky Survey and the upcoming Vera Rubin Observatory are cataloguing millions of galaxies. Hidden among them, there may be more Hoag-like objects waiting to be recognized. Each discovery could tip the balance between coincidence and hidden physics. If we find 10, 100, or 1,000, the odds shift dramatically. What looks like chance in one case begins to look like a pattern in many. In the meantime, theorists run simulations trying to reproduce Hoag's object on computer screens. They adjust dark matter halos, gas flows, collision angles, and star formation rules, looking for the rare combination that produces a golden core, an empty gap, and a luminous ring. If the simulations succeed, then physics is enough. If they fail, then coincidence regains its strength. So far, success has been limited. Models can produce rings, but not ones as clean as Hoag's object. That gap between model and reality is what keeps astronomers intrigued. There is also a philosophical layer to this debate. Humans are pattern seekers. We are uncomfortable with randomness, always looking for meaning. When we see Hoag's object, we want to believe it reveals hidden physics, because that feels purposeful, explainable, satisfying. To accept coincidence feels anticlimactic, and yet, the universe has no obligation to provide meaning. Sometimes things just happen. Sometimes a galaxy looks strange because the dice of gravity rolled that way. The challenge is to separate our desire for explanation from the actual evidence. And yet, even if Hoag's object were a coincidence, it would still matter. Coincidences themselves can be instructive. They show us the range of possibilities, the edges of what can happen. They remind us that the universe is vast enough to allow for exceptions. If Hoag's object is one of those exceptions, it is still valuable. It expands the gallery of galactic forms, reminding us that not everything fits the categories. But if it is hidden physics, then the stakes are higher. That would mean there are processes at work in galaxies that we have not yet identified. It would mean our models of star formation, gas dynamics, or dark matter are incomplete. And that would be exciting because it would point the way to new discoveries. Science grows not only by confirming what we expect, but by stumbling over what we don't. Hoag's object could be one of those stumbles, one that forces us to look harder, to refine our theories, and to admit how much we don't know. So the question lingers. Is this galaxy a rare accident, or is it a signal? The truth may take decades to uncover. It may require more observations, better simulations, and perhaps even new kinds of telescopes. For now, we stand between two possibilities, each humbling in its own way. Coincidence reminds us of the universe's scale, its ability to produce wonders simply by chance. Hidden physics reminds us of our ignorance, the vast territory of knowledge we have not yet explored. In either case, Hoag's object holds its place in the sky, glowing quietly, asking its question without offering an answer. When astronomers first puzzled over Hoag's object, one of the obvious questions was whether it really was unique, or if there might be others like it scattered across the sky. After all, rings do exist in galaxies, even if they are rare. If Hoag's object had siblings, perhaps they could help explain its origins. And indeed, there are other galaxies with rings. But when you line them up side by side, none of them quite match Hoag's eerie perfection. Instead, they look like imitations, echoes of the same idea, close enough to remind us of the possibility, but different enough to leave Hoag's object standing alone. The most famous of these is the Cartwheel Galaxy. Its image has been published in textbooks, plastered on posters, and studied in detail for decades. It sits about 500 million light-years away, roughly the same order of distance as Hoag's object, and its structure is striking. A central hub, a bright ring, and faint spokes that radiate outward. The ring of the cartwheel glows with newborn stars, created in a burst of star formation triggered by a collision. Astronomers are confident that another galaxy passed through it, like a stone through a pond, sending ripples that form the ring. The evidence is clear, the mechanism understood. But when you look closely, the cartwheel is not smooth. Its ring is jagged, broken into clumps and arcs, its symmetry disrupted by the violence of its creation. The spokes are uneven, scars of the impact. Compared to Hoag's object, the cartwheel looks like a ring forged in chaos, not in order. Other examples are less famous but follow similar patterns. Galaxies catalogued in surveys occasionally show ring-like features, often produced by resonances in barred spirals. In these cases, the ring encircles the bar, formed by the orbital dynamics of stars and gas. These resonance rings can be striking, but they are never as detached as Hoag's. The bar cuts through the middle, connecting the core to the ring, destroying the illusion of isolation. They are beautiful in their own way, but they do not have the same clean emptiness that makes Hoag's object so unsettling. There are also polar ring galaxies, a category of systems where a ring of gas and stars orbits at right angles to the main galaxy. These are thought to form when a galaxy captures material from a companion, which then settles into a perpendicular orbit. Polar ring galaxies look strange with their cross-shaped structures, but once again they are messy. The rings are tilted, warped, uneven. They do not achieve the symmetry of Hoag's object, nor its sharp separation between core and ring. Astronomers sometimes mention a few other galaxies that resemble Hoag's more closely. In deep surveys, a handful of systems show central bulges with surrounding rings, and some even appear nearly circular. But when you zoom in, the differences emerge. The rings are not as smooth, the gaps are not as empty, the cores are not as centered. They look like attempts at the same design, but none quite succeed. It is as though nature tried several times, came close, but only once drew the circle to perfection. This raises an interesting possibility. If Hoag's object is not truly unique, but rather an extreme case of a rare type, then studying its imitators could help. By comparing the less perfect rings to the flawless one, astronomers might identify the key factors that make the difference. Perhaps the others are younger or older, caught in different stages of evolution. Perhaps they formed through similar mechanisms but under less precise conditions. If so, then Hoag's object could be the ideal example, the textbook case, while the others are incomplete or imperfect versions. But the danger is that comparisons can sometimes obscure the uniqueness rather than explain it. If you lump Hoag's object in with other rings, you risk assuming it belongs to a category when in fact it does not. That tension is part of why it continues to fascinate scientists. It looks like a ring galaxy, but it does not behave like one. It looks like it belongs to a type, but it refuses to follow the rules of that type. The imitators highlight the contrast rather than soften it. The comparison also underscores just how rare rings are in the first place. Out of the hundreds of billions of galaxies in the observable universe, only a small fraction show ring-like structures, and among those only a handful approach the symmetry of Hoag's object. This rarity amplifies its strangeness. If rings were common, Hoag's might be seen as just an extreme example, but because rings themselves are rare, Hoag's becomes doubly exceptional, rare among the rare. It's worth noting too that our perspective shapes what we see. From Earth, we view Hoag's object almost face-on, so the ring looks perfectly circular. If it were tilted, we might not even recognize it as unusual. The same is true of other galaxies. Some that look irregular from our angle might in fact have hidden rings, obscured by perspective. This means that part of what makes Hoag's object unique is not just its structure, but our vantage point. Out of all the galaxies in the sky, we happen to see this one from just the right angle to reveal its perfection. That too feels like coincidence, or perhaps fate, depending on how you look at it. The imitators also remind us that galaxies are snapshots in time. Rings evolve, they expand, disperse, and fade. The cartwheel will not always look as it does. Its ring will eventually dissolve, its spokes will scatter, and it will become something else. Perhaps Hoag's object itself is caught in a fleeting phase, one that will not last. If we could watch for another billion years, maybe the ring would fade and the gap would fill in, leaving behind a more ordinary galaxy. If that is true, then the imitators are not failed attempts but different moments in the same process. We're just catching Hoag's at the most photogenic stage. Still, even if time plays a role, the comparison holds. Hoag's object looks different from the rest. Its symmetry is unmatched. Its gap is cleaner. Its contrast between core and ring is sharper. That is why, despite decades of searching, astronomers continue to treat it as one of a kind. The imitators prove that rings are possible, but only Hoag shows us what happens when the universe draws a perfect circle. And so, as telescopes sweep the skies and catalogue millions more galaxies, astronomers keep looking for another like it. If one is found, it will not erase Hoag's uniqueness, but it may help us understand it. Until then, the imitators serve as a backdrop, a gallery of almosts, against which Hoag's object shines all the more brightly. When we look at Hoag's object through our telescopes, what we see is not the galaxy as it exists today. We are seeing it as it was 600 million years ago, because that is how long it has taken for its light to travel across the depths of space to reach Earth. This simple fact is both ordinary in astronomy and deeply astonishing when you stop to consider it. Every star, every galaxy, every glimmer in the night sky is a messenger from the past. But the farther away the object, the further back in time we are peering. With Hoag's object, we are not looking at something as it is, but at something as it once was, long before human beings even existed on this planet. 600 million years is a span so vast that it almost slips through the mind without leaving an impression. On Earth, that timescale carries us back into an alien world. The continents were arranged differently. The atmosphere was not the same, and life itself was in a very different stage of development. The first simple animals were only just beginning to spread in the oceans. Plants had not yet taken root on land, and the air was thick with carbon dioxide. Dinosaurs were still hundreds of millions of years in the future. The light that now enters our telescopes began its journey back then, leaving the young stars of Hoag's ring and racing outward into the dark, across unimaginable gulfs of nothing, until at last it brushed against our world. This is one of the strange gifts of astronomy. It allows us to see history without books or fossils, by capturing photons that have carried stories for eons. When we observe Hoag's object, we are in conversation with a time so distant that our own species is a latecomer. Every twinkle of light from the galaxy is older than humanity itself. That thought is humbling, but also comforting in its own way. It places us in a vast timeline, one that dwarfs our troubles and reminds us that we are only a small part of something immense. The distance to Hoag's object also highlights the incredible sensitivity of our instruments. A photon of light is a tiny thing, but it can survive 600 million years of travel, crossing cosmic voids, dodging galaxies and dust, and still arrive at Earth intact. Think of that for a moment. These particles of light were emitted before there were mammals, before there were forests, before the continents of Earth took their modern shape. They travelled longer than the age of the dinosaurs, longer than the rise and fall of entire mountain ranges, and yet, tonight, they slip into our telescopes as if no time had passed at all. This is why astronomers sometimes say telescopes are time machines. They do not transport us physically into the past, but they allow us to see it directly. The farther away the object, the deeper the look into history. Nearby stars show us what happened a few years ago. Distant galaxies show us what happened millions or billions of years ago. In the case of Hoag's object, the image we see now is a portrait of a galaxy long gone, at least in that form. For all we know, Hoag's object today might look different. Its ring may have evolved, its stars may have shifted, its symmetry may have faded. We cannot know until its present light, still on the way, reaches us millions of years from now. This creates a strange sense of distance, not just in space but in time. When we look at Hoag's object, we're not sharing the present with it. We're separated by a gulf so wide that even light cannot cross it quickly. To see it as it is now would require us to wait 600 million years or to find a way to leap across the intervening space. That separation is permanent. We will always see it as it was, never as it is. And yet that distance does not diminish its beauty. In fact, it enhances it. The knowledge that the light is ancient gives it weight. It is not just a picture of a galaxy, it is a relic of time. Every detail, from the golden core to the blue ring to the empty gap, is a snapshot of history frozen in photons. We are not seeing the galaxy live but preserved, like a fossil in stone. Only here the fossil is made of light and the stone is the universe itself. This concept of light as history applies not just to Hoag's object, but to everything in the night sky. The moon, only a light second away, shows us its face as it was a moment ago. The sun, 8 light minutes away, shows us what it was doing 8 minutes earlier. The nearest star, Proxima Centauri, reveals itself as it was 4 years ago. The Andromeda Galaxy, our neighbouring spiral, appears as it was more than 2 million years ago. Each object is delayed by the time it takes light to travel. The farther we look, the older the images become. In that sense, astronomy is always archaeology, except the ruins we study are scattered across space instead of buried in the ground. For Hoag's object, the delay is so immense that it stretches the imagination. Think of what Earth has been through since the light left that galaxy. Continents drifted, climates shifted, mass extinctions wiped out species, others rose in their place, dinosaurs appeared, ruled the planet, and vanished. Mammals emerged, evolved, spread, and eventually gave rise to humans. Civilizations rose and fell. Languages were spoken and forgotten. And through it all, those photons sped silently across the void, carrying their message of a perfect ring and a golden core. Only now do we receive them, and only now do we marvel. The distance also means that Hoag's object is not just far away, but deeply inaccessible. 600 million light-years is beyond any practical journey. Even if we built a spacecraft travelling close to the speed of light, it would take longer than all of human history to arrive. In practice, Hoag's object is forever out of reach. We can look, we can study, we can model, but we cannot touch. It is a reminder that most of the universe is not for us to visit, only to observe. And perhaps that is enough. Sometimes it is enough to know that something exists, even if we can never go there. From a scientific standpoint, the distance matters because it helps us place Hoag's object in context. By measuring its redshift, the stretching of its light caused by the expansion of the universe, astronomers can confirm how far away it is and how fast it is receding. This data not only tells us about the galaxy itself, but also helps refine our understanding of cosmic expansion. Every distant object contributes to the larger picture of how the universe grows. Hoag's object, with its peculiar shape, is still part of that broader pattern. But beyond the science, the distance is a source of wonder. To think that our small planet, circling a modest star on the edge of an ordinary spiral galaxy, can detect light from a system so far away is almost miraculous. We are tiny, fragile creatures, yet we have built instruments capable of catching whispers from the deep past. Hoag's object is not just an object of study, it is a symbol of our ability to reach across time and space with nothing more than curiosity and ingenuity. And so, when you look at the image of Hoag's object, remember that it is not simply a picture, it is a message from another era, a relic of a world that existed long before we did. The galaxy you see may no longer look that way. Perhaps its ring has dispersed, its stars have changed, its symmetry has broken, or perhaps it remains as it was, still defying our expectations. We cannot know. All we can do is marvel at the fact that the universe allows us even this glimpse, this chance to see across time, to look 600 million years into the past and to wonder what stories the galaxy might still hold in its present, waiting for future light to carry them toward us. When the Hubble Space Telescope first captured a clear image of Hoag's object, astronomers were already prepared for its strange symmetry. They knew about the golden core, the empty gap, and the luminous blue ring. But what none of them expected was the surprise hidden in plain sight, right in the hollow middle of the galaxy. Nestled inside the dark band, perfectly aligned with the central sphere, was another ring galaxy, far more distant, seen through the window of Hoag's object like a framed picture hanging in the sky. It is easy to miss on a casual glance. Your eyes are drawn to the bright structures of Hoag's object itself, and only after staring for a while do you notice the faint circle within the hollow. But once you see it, the effect is uncanny. One ring galaxy is strange enough, but here is another, smaller and fainter, positioned with eerie precision in the one spot that makes the entire composition look deliberate. A galaxy within a galaxy, a window within a window. The odds of such an alignment are staggering. Space is vast and galaxies are scattered across it in every direction. The chance that one distant ring galaxy would happen to line up exactly with the empty gap of another, as seen from Earth, is vanishingly small. And yet, that is what we see. It is almost as though the universe is playing a trick, or leaving a signature, or reminding us that coincidence and improbability are built into its design. For astronomers, the sight is both delightful and unsettling. It is delightful because it makes the image of Hoag's object even more beautiful, like a painting with an unexpected detail. It is unsettling because it looks so purposeful when, in all likelihood, it is not. This distant galaxy is far behind Hoag's object. It has nothing to do with it physically. They are not interacting, not bound by gravity, not connected in any way. It just happens to lie along the same line of sight. Light from that faraway ring has travelled even longer than the light from Hoag's object, perhaps hundreds of millions of years more, and in the final moments of its journey, it passed through the space between the stars of Hoag's empty gap and continued onward to us. If Hoag's object were tilted at a different angle, we would never have noticed. If the tiny background galaxy had been slightly off-centre, it would not look so perfectly framed. The alignment is pure chance, and yet it is the kind of chance that makes the universe feel playful. When astronomers share the Hubble image of Hoag's object, they often point out this tiny feature, as though it were a secret hidden inside the picture. It reminds us that the universe contains layers upon layers of structure, and that when we gaze at one galaxy, we're also gazing through it, into the depths beyond. Every window in the cosmos looks onto another, and sometimes the alignments create patterns that seem too precise to be random. This little galaxy also underscores how deep the universe is. Hoag's object itself is 600 million light-years away, and the smaller ring galaxy behind it is even farther. Looking at them together is like looking through layers of history, each one older than the last. The light from the tiny background galaxy left its stars long before the light from Hoag's object did. By the time those photons began their journey, the Earth was even younger, life more primitive, the continents arranged differently. Now those two separate histories converge in a single photograph, overlapped by nothing more than our line of sight. Some astronomers have mused that this alignment is almost cruel in how tantalizing it feels. Imagine if the smaller galaxy could be studied in detail, framed as it is by Hoag's object. But because it lies so far away, it is faint, and even our best telescopes can only glimpse its outline. We see the ring, but not much more. It is like a distant painting glimpsed through a window, too far to study closely. And yet, even that faintness adds to the sense of wonder. The fact that we can see it at all is extraordinary. Its photons have crossed unimaginable distances, dodged stars and dust, travelled for hundreds of millions of years, and still managed to pass through the hollow of another galaxy and arrive intact. For people looking at the image for the first time, this small detail often triggers a double reaction. First comes awe at the beauty of Hoag's object itself. Then comes a second wave, when they realise that the dark centre is not empty after all. That tiny extra galaxy is like a whisper, a reminder that even in the most mysterious structures, there are deeper mysteries waiting. The universe rarely gives us one wonder at a time. It stacks them one behind the other, like nested dolls, each hidden within the other until we notice. The alignment also illustrates something profound about astronomy. We never see only one object. Every telescope image contains layers of distance. Nearby stars shine in the foreground, galaxies drift behind them, and still farther galaxies hide behind those. If we stare long enough, as with the Hubble Deep Field images, we can see thousands of galaxies packed into a single frame, each at a different distance, each at a different stage of cosmic history. Hoag's object, with its inner window, is a small-scale version of that principle. It shows us two galaxies at once, separated by hundreds of millions of light-years, but aligned by perspective into one breathtaking composition. It is tempting to read symbolism into this. The tiny background galaxy framed within Hoag's object is like a message about infinity, a reminder that no matter how far we look, there is always farther still. Beyond every horizon is another horizon, beyond every galaxy is another, and sometimes, by pure chance, they line up in ways that make us stop and marvel at the coincidence. It is humbling, but also strangely comforting to realize that the universe has layers upon layers, and that our telescopes are just beginning to peel them back. And then there is the simple aesthetic effect. Hoag's object is already a near-perfect circle, but with the smaller ring inside it looks almost designed. Some have compared it to a cosmic bullseye, others to an eye staring out of the darkness, others to a celestial target painted across space. The inner galaxy completes the illusion. Without it, Hoag's object would already be uncanny. With it, it becomes surreal, as though the universe wanted to make sure we paid attention. Of course, astronomers resist such language. They remind themselves that this is coincidence, not intention. The smaller galaxy has no relationship to Hoag's object, and its placement is only a trick of perspective. But even scientists are human, and many admit to feeling a thrill when they first noticed it. The odds are so low, the effect so strange, that it is hard not to smile at the discovery. In science, wonder is not a weakness. It is often the spark that drives curiosity forward. So the tiny galaxy inside the ring is more than just a background object. It is part of the story of Hoag's object. It adds another layer of mystery, another reason why this one galaxy stands out from the countless billions. It reminds us that the universe is not neat, but it can be playful. It reminds us that perspective shapes what we see, and that sometimes the most astonishing alignments are simply chance. And it reminds us that behind every object we study, there is always more waiting, deeper, older, and farther away. When astronomers are confronted with something that doesn't fit their categories, their instinct is not to shrug and walk away. Their instinct is to explain. Hoag's object, with its golden core, empty gap, and perfect ring, has inspired decades of speculation. If it doesn't look like the aftermath of an ordinary collision, then maybe it's something else. And so, theory after theory has been proposed, each one attempting to bring the galaxy back into the fold of our understanding. Some are grounded in well-tested physics, others lean into more speculative territory. None have yet solved the riddle entirely. The first and most obvious idea is the collision model. We know that when galaxies collide, they can form rings. The smaller intruder plunges through the larger galaxy's disk, sending out a density wave that compresses gas into a circular front. This model explains many ring galaxies, including the famous Cartwheel Galaxy. It's neat, it's supported by simulations, and it fits with the idea that the universe is shaped by encounters. So naturally, astronomers try to apply it to Hoag's object. Perhaps a small galaxy passed through the centre long ago, creating the ring we see today. but the details don't fit. In collisional rings, the core is usually disturbed, scarred by the impact. In Hoag's object, the core is smooth and round. In collisional rings, the outer circle is messy, full of irregular clumps and asymmetries. In Hoag's object, the ring is near perfect, and collisional rings often have nearby companions that can be identified as the intruder. Hoag's object has none. If a collision did occur, it must have been so ancient or so precise that it erased every trace of violence and left behind only serenity. That is possible, but it stretches the model thin. The next theory turns to accretion. Galaxies are not closed systems. They feed on gas from the cosmic web, streams of hydrogen that thread the universe in vast filaments. If Hoag's object captured gas from its environment, that gas could have settled into a circular orbit, forming stars only in the outer regions. This could explain the youth of the ring and its ongoing star formation. It might also explain the empty gap. If gas never reached the inner regions, then stars could not form there. The trouble is, accretion usually produces disks, not rings. Gas tends to settle throughout, forming spirals or irregular patches. For accretion alone to produce such a sharp circle, conditions would need to be incredibly specific. Another idea involves resonance. Just as gravitational resonances carve gaps in Saturn's rings, or in the asteroid belt of our solar system, resonances within galaxies can redistribute gas into ring-like shapes. In barred spiral galaxies, for example, the bar can drive gas outward, piling it up into a ring. Could Hoag's object be the product of such a resonance? The problem is that it lacks a bar. Its core is too round, too featureless. Without a bar, resonance doesn't have an obvious driver. Unless the bar once existed and later dissolved, leaving only the ring behind, this explanation falls short. Then there is feedback from the central black hole. We know that the supermassive black holes at the centres of galaxies can influence star formation on enormous scales. As they feed on gas, they release powerful outflows of energy, sometimes sweeping material out of the core and preventing new stars from forming. Perhaps in Hoag's object, the black hole blew out the gas from the middle, clearing the gap while leaving enough material farther out to form the ring. This could explain the emptiness, but would it create such a symmetrical ring? Feedback is usually messy, creating bubbles, lobes, or irregular shells. Once again, the elegance of Hoag's object seems to resist the chaos expected of the process. One of the stranger proposals came early on, before astronomers had high-resolution images, when some wondered whether Hoag's object might not be a ring galaxy at all, but an illusion. Perhaps it was a case of gravitational lensing, where the gravity of a massive object bends light from a background galaxy into a ring. Such Einstein rings do exist. They are rare, but they are known. Could Hoag's object be one of them? The idea was tantalizing. The golden core could be the lensing galaxy, and the blue ring could be the light of a more distant system distorted into a circle. But this theory was eventually ruled out. The spectra of the core and the ring show that they are at the same distance, part of the same structure, not foreground and background. Hoag's object is not a lens. It is truly what it appears to be, a galaxy with a real ring. Still, the lensing hypothesis lingers in the imagination, because it reveals how desperate astronomers were to make sense of the sight. When confronted with something that looks impossible, our minds reach for illusions. We suspect a trick, a distortion, a misunderstanding. The fact that Hoag's object is real makes it even more confounding. Other models try to combine processes. Maybe Hoag's object began as an elliptical, which then captured gas in a perfectly circular orbit, creating the ring. Or maybe a small collision triggered the ring, and then gas accretion sustained it. Or maybe resonances helped maintain it once it formed. Each of these hybrids tries to cover the gaps left by the simpler theories, but they all share a problem: the need for precision. To get Hoag's object, everything must line up just right. The collision must be exact, the gas must fall in evenly, the resonance must act in harmony. It feels like a conspiracy of circumstances, too neat to be likely, and yet undeniably there in the sky. What makes this discussion fascinating is not just the theories themselves, but the way they expose the limits of our knowledge. Every galaxy is the product of the same physics: gravity, gas dynamics, star formation, dark matter. And yet those ingredients can arrange themselves into forms we didn't predict. Hoag's object shows us that our recipes are incomplete. We know the ingredients, but not all the ways they can be combined. It's as if we thought we understood how to bake bread, and then the universe handed us a cake, asking us to explain how it was made from the same flour and water. And so, the theories pile up: collisions, accretion, resonance, feedback, lensing, hybrids of all kinds. Each one has strengths, each one has weaknesses. None is entirely convincing. That is the state of Hoag's object today. Not unexplained, but underexplained. We have ideas, but not certainty. We have models, but not matches. We have guesses, but not proofs. The search for explanation continues, because that is what science does. Astronomers run simulations, adjust parameters, look for analogues, and scan the skies for more examples. Theories that fail today may succeed tomorrow, with new data. What feels impossible now may one day feel obvious. But until then, Hoag's object remains the galaxy that refuses to sit still, the one that keeps slipping through the cracks of our categories, the one that resists the tidy stories of cosmic evolution. The history of science is filled with puzzles that resist tidy answers, objects and phenomena that sit stubbornly at the edges of understanding. Hoag's object has become one of those puzzles. For decades, astronomers have tried to fold it into the categories they know: collision, accretion, resonance, lensing, feedback, or some mix of these. Each theory carries weight, each explains a piece of the story, but none of them explain the whole. Every model runs into problems, every neat picture frays at the edges, and the galaxy itself remains aloof, as though quietly defying the efforts to be understood. Take the collision theory. It works beautifully for other ring galaxies. We have photographs of them. We have simulations that recreate them. We have the physics that supports them. A small galaxy plunges through a larger one, and a ring of star formation expands outward. The Cartwheel Galaxy is the poster child for this model, and it fits perfectly. But when we turn to Hoag's object, the same model falters. Where is the distortion in the core? Where are the tidal tails, the streams of debris, the nearby companion that triggered the event? They are not there. Perhaps the collision happened so long ago that the scars have faded. That's possible. But if it was that long ago, the ring should have aged, its blue stars should have burned out, its structure should have dispersed. Instead, the ring still glows with youth, still holds its shape. The timing doesn't add up. Accretion sounds promising at first. Galaxies are not closed islands. They gather gas from their surroundings, pulling in streams of hydrogen from the cosmic web. If Hoag's object captured gas in just the right way, maybe it formed a ring. This could explain why the ring is still producing young stars today. But why would the gas fall only into the ring, and not into the core? Why would it arrange itself into such a smooth, perfect circle, instead of the patchy disks and spiral structures we usually see? Accretion tends to be messy, driven by uneven flows of gas and gravity. It does not normally create geometric precision. Resonance also has an allure. In barred spirals, resonances can push gas outward into rings. The dynamics of rotation and gravity create stable zones where material piles up, while other regions are cleared. This mechanism explains inner and outer rings in many galaxies. But Hoag's object lacks the one. Feature resonance depends on a bar. Its core is smooth and spherical, showing no trace of a bar that could have driven the process. Maybe the bar once existed and later dissolved. That could happen, but there's no sign of it, no remnant. And again, resonance usually produces partial rings, arcs, or multiple structures, not the isolated perfection we see here. Black hole feedback is another candidate. We know that the supermassive black holes at the centers of galaxies can shape their environments, blasting out gas, creating cavities, and influencing star formation on scales of thousands of light years. Could Hoag's black hole have cleared the gap, forcing star formation into the ring? It's possible, but feedback is messy. It produces bubbles, jets, irregular shells. It does not produce perfect circles. To get the structure we see in Hoag's object, the feedback would need to be fine-tuned to an extraordinary degree far beyond what we've observed in any other galaxy. The gravitational lensing hypothesis is one of the more imaginative. If Hoag's object were not really a ring at all, but instead the distorted light of a background galaxy bent into a circle by the gravity of a closer one that could explain the symmetry. Einstein's equations predict such rings, and astronomers have observed them elsewhere. But this theory collapses when you check the data. The core and the ring are at the same distance, part of the same galaxy. They are not foreground and background. Spectroscopy settles that. Hoag's object is real, not an illusion. Hybrid theories try to stitch these explanations together. Maybe a collision started the process, and then accretion sustained it. Maybe a bar once existed, then dissolved, leaving the ring behind. Maybe feedback from the black hole cleared the gap while other processes maintained the symmetry. These multi-step stories are creative, but they become increasingly convoluted. The more conditions you add, the less likely the scenario becomes. It starts to feel like bending the rules of physics around one object, rather than the object fitting into the rules. The deeper problem is that every theory fails on the same point: precision. The universe is messy. Collisions are chaotic. Accretion is uneven. Feedback is turbulent. Resonances produce irregularities. Nature rarely draws straight lines or perfect circles. Yet Hoag's object is precise. Its ring is smooth. Its gap is clean. Its core is round. Its symmetry is uncanny. The very perfection of the structure is what defeats the models. Every known process produces some level of disorder, but here the disorder is absent. This is why astronomers sometimes joke that Hoag's object looks too perfect. It looks less like the product of natural processes and more like a diagram in a textbook. But that cannot be right. It is natural, it is real, and it exists within the laws of physics. The question is whether those laws, as we currently understand them, are enough to explain it. The failure of every theory does not mean the galaxy is unexplainable. It means our understanding is incomplete. Perhaps the models we have are correct in principle but missing details. Perhaps collisions can produce cleaner rings than we think, under very specific conditions. Perhaps accretion can settle into circles if guided by the right dark matter distribution. Perhaps feedback can be more symmetrical under circumstances we haven't yet observed. The galaxy might not defy physics, but it may be reminding us that physics is broader than the cases we've studied so far. And so, astronomers keep trying. They run simulations with finer resolution, they test new models, they search for more galaxies like Hoag's. Each failure is not wasted effort, but part of the process. Science often advances not by solving puzzles immediately, but by narrowing the possibilities, ruling out the simple explanations, and forcing us to think deeper. Hoag's object is valuable precisely because it refuses to fit. It is a reminder that the universe is more creative than our categories. The problem with every theory, then, is not just that it fails to explain Hoag's object. The problem is that it fails to explain why such perfection should exist at all. If the galaxy were messy, we could tuck it into a box, call it a collisional ring, and move on. But its symmetry demands more. It demands either an extraordinary coincidence, a rare balance of forces or physics we have not yet identified. None of those answers are comfortable, but they are all fascinating. When astronomers study galaxies, they are not just cataloguing shapes, they are reading histories. Each galaxy is the outcome of billions of years of events, collapses of gas clouds, bursts of star formation, collisions with neighbours, quiet periods of growth. Every spiral arm, Every central bulge, every faint halo of stars carries the record of what has happened before. To look at a galaxy is to see a story written in light, a story that began long before our world existed. Most galaxies tell stories we've learned to recognize. A barred spiral shows us a tale of ordered rotation, of stars and gas flowing along density waves, of structures sustained by balance. An elliptical shows us the aftermath of violence, the end product of mergers, its stars thrown into random orbits by the chaos of past collisions. An irregular shows us a tale of disruption, a smaller system battered by forces larger than itself. Each one fits into a pattern, a genre of story that we can read and understand. But then there are galaxies like Hoag's object, whose stories seem to resist interpretation. It presents us with a golden core, an empty gap, and a luminous ring, but the narrative is unclear. Was this once an ordinary galaxy, disrupted by a collision so long ago that all evidence has been smoothed away? Was it fed by streams of gas that, by coincidence or by hidden laws, settled into a circle instead of a disk? Is it a snapshot of a fleeting phase or a long-lived equilibrium we don't yet understand? The story is there, written in its stars, but we do not yet know the language. That uncertainty is what makes it valuable. Galaxies like Hoag's object expand our sense of possibility. They remind us that the universe is not bound to the categories we create. It writes its stories in ways we did not anticipate, forcing us to expand our interpretations. Hoag's object tells us that there may be more kinds of galactic histories than we have yet imagined. It may be one of a kind, or it may be the first known member of a hidden class. Either way, it whispers that our story of galaxies is not finished. In a way, this is how science always works. We build models based on what we observe, and then the universe shows us something new that doesn't fit. The new thing is not a mistake, it is an invitation. It is a clue that our models are partial, our understanding incomplete. Hoag's object is one of those clues. It is an exception that asks us to revise the rules, and in doing so, it tells us something about the universe itself, that it is endlessly creative, endlessly varied, and never exhausted by our categories. Galaxies are also stories of time. Each one contains stars of many ages, from newborn giants to ancient dwarfs that have burned for billions of years. By studying the colours and distributions of those stars, astronomers can reconstruct the timeline of the galaxy, when its stars formed, when bursts of activity occurred, when collisions happened. In Hoag's object, the contrast between the old golden core and the young blue ring is stark. It is like reading 2 chapters of a book with all the pages in between missing. The gap is not just spatial, it is temporal. The galaxy tells us there was an old beginning, and there is a young present, but the middle of the story is absent. That absence is itself part of the narrative, a missing piece that makes the whole more mysterious. In the broader context, galaxies tell the story of the universe as a whole. The first galaxies formed when the universe was only a few 100 million years old, small and irregular. Over time, they merged and grew, evolving into the spirals and ellipticals we see today. By studying galaxies at different distances, we can trace this history, because distance is also time. Nearby galaxies show us the present, distant galaxies show us the past. Together, they reveal a timeline of cosmic evolution, from the first faint clumps of stars to the vast structures of today. Where does Hoag's object fit into that story? In some ways, it resists placement. It looks ancient and young at once, settled and dynamic, ordinary and extraordinary. It may be telling us that our story of galactic evolution is too simple, that there are branches we have not yet explored. Perhaps rings like this are more common than we know, hidden among the billions, waiting to be found by deeper surveys. Or perhaps it is a true outlier, a single unusual story that proves the universe is capable of surprises. In either case, it is part of the larger narrative, the narrative of diversity, of exception, of the universe's refusal to be predictable. There is also a human layer to this. Galaxies are stories not just in themselves, but in how we encounter them. For Arthur Hoag, who first discovered this object in 1950, the story was one of curiosity, noticing something strange in a photographic plate and wondering what it could be. For astronomers who studied it in later decades, the story was one of classification and frustration, trying to fit it into categories and failing. For the public, when the Hubble Space Telescope revealed its full beauty, the story became one of wonder, spreading across the internet as people marveled at its symmetry. Each generation adds its own chapter to the story of Hoag's object, not in the galaxy itself, but in our relationship with it. This is what makes galaxies so profound as symbols. They're both distant and intimate. They're far beyond our reach, yet we weave them into our understanding of who we are. Hoag's object is not just a physical system of stars and gas. It is also a mirror of our questions, our limits, our imagination. It tells us that the universe contains things we cannot yet explain, and in doing so, it teaches humility. Sometimes, astronomers speak of galaxies as fossils. They are relics of past conditions preserved across time. But fossils are usually static, while galaxies are dynamic. They change, evolve, and tell ongoing stories. Hoag's object may evolve too, its ring dispersing, its core merging with the outer stars, its symmetry dissolving. Millions of years from now, it may look ordinary. What we see today may be a temporary chapter, caught at just the right moment. If so, we are lucky to witness it. But even if it changes, its story will remain. Because the light we see now has already left, already travelled 600 million years to reach us. Whatever Hoag's object has become since then, the version we know is preserved forever in the photons that continue to stream toward Earth. In that sense, the story is both fleeting and permanent. The galaxy evolves, but the light we have captured freezes one moment forever. So what does Hoag's object tell us about the universe? It tells us that the universe is capable of more than we expect. It tells us that symmetry, though rare, is possible. It tells us that gaps in our knowledge are as important as the knowledge itself. And it tells us that beauty is not separate from science, but part of it, that wonder and curiosity are as essential to astronomy as equations and models. When you think about the history of science, it's often the exceptions that capture our imagination. The things that don't fit, the anomalies that resist explanation, the quiet reminders that the universe is always more complicated than the categories we make for it. Hoag's object is one of those exceptions, and while astronomers wrestle with equations and simulations to make sense of it, the rest of us feel something deeper, a kind of wonder that arises not from clarity, but from mystery. Humans love patterns. We find comfort in rules, in symmetry, in predictability. But we also love the things that break those rules. We are fascinated by the rare, the unusual, the one-off examples that stand out against the background. This is true in art, in nature, and in science. A spiral galaxy is beautiful, but a galaxy that looks like no other, one that seems almost designed, pulls at something inside us. It is the difference between seeing a familiar landscape and stumbling upon a strange formation that seems to defy geology. It is the difference between hearing a well-known piece of music and hearing a new note that shouldn't exist, but does. Part of the appeal lies in rarity itself. When something is common, we enjoy it, but it fades into familiarity. When something is rare, it feels like a secret, a treasure. Hoag's object is rare even among rare things. Ring galaxies are already unusual, and among them, this one is almost unique. To see it is to know that you are witnessing something most galaxies never become, something extraordinary against a backdrop of billions. That rarity stirs curiosity. It makes us lean closer, wanting to understand, but also wanting to simply marvel. There is also a deeper psychological pull. Exceptions remind us that the universe is not finished, that there are still mysteries left. In a world where we sometimes fear that everything has already been explained, that science has left no room for wonder, objects like Hoag's show us that the unknown is alive and well. They reassure us that discovery is not over, that there are still secrets hidden in the stars. For scientists, this is motivating. For everyone else, it is comforting. The universe is not a closed book. It is a library with endless volumes, some of which we have not even begun to open. Hoag's object also taps into our love of symmetry and perfection. We are drawn to circles, to patterns that feel intentional. When we see the golden core and the blue ring separated by a dark gap, it looks like a design, a symbol. Our minds instinctively search for meaning. We imagine eyes, targets, halos. We give it metaphors because the raw shape is so striking, and yet we know it is natural, not designed. That tension between what looks intentional and what is actually accidental is part of what makes it compelling. It shows us that beauty can arise without purpose, that order can emerge from chaos. At the same time, the human response to Hoag's object is not just about aesthetics, it's also about humility. When we confront something we cannot explain, we are reminded of our limits. We are reminded that even with our telescopes and models, we do not yet know everything. For some, that might be frustrating. But for many, it is exhilarating. Mystery is not an obstacle, but an invitation. It is a reason to keep looking, to keep asking, to keep learning. Hoag's object is humbling, but in a way that inspires rather than diminishes. There is a long tradition of anomalies driving science forward. The orbit of Mercury didn't fit Newton's laws, and that anomaly led eventually to Einstein's theory of relativity. The spectrum of light from stars didn't fit known chemistry, and that anomaly led to the discovery of nuclear fusion as the power source of stars. Time and again, the exceptions have become the keys to deeper truths. Perhaps Hoag's object is one of those keys. Perhaps by refusing to fit, it will one day open the door to a new understanding of galaxies, or of dark matter, or of cosmic evolution. Even if it doesn't, even if it remains an oddity, it still serves a purpose. It reminds us not to be complacent. Beyond science, there is also something deeply personal in the way we respond to such objects. Many people, when they first see the image of Hoag's object, feel not just curiosity but a kind of quiet awe. It is beautiful, yes, but it is also strange, and that strangeness sparks reflection. We think about how small we are, how vast the universe is, how unlikely it is that we're here to witness such things at all. The galaxy becomes not just an astronomical object, but a mirror for our own sense of existence. It makes us feel both tiny and connected, both insignificant and part of something greater. And then there is the simple joy of wonder. Wonder is not always about answers. Sometimes it is about questions. Sometimes it is about sitting with the mystery, letting it wash over you, enjoying the fact that the universe still has the power to surprise. Hoag's object does that. It surprises, it resists, it delights. It tells us that not everything is solved, and that the cosmos is still full of secrets waiting to be uncovered. This is why exceptions to the rules matter. They are not just curiosities. They are the places where our imagination and our science meet. They are the places where we remember that knowledge is not a wall, but a horizon, always moving as we approach it. Hoag's object sits on that horizon, a reminder that there is more out there than we can currently explain, and that perhaps is the most human reason of all to love it. As we come back from this long journey through Hoag's object, it's worth pausing to feel what lingers. We've wandered through the golden glow of its core, circled the blue ring of newborn stars, drifted across the empty gulf that separates them, and tried to follow the many theories that rise and fall in their attempts to explain it. We've looked back through hundreds of millions of years of time, glimpsed a smaller galaxy peering out through the hollow centre, and wrestled with the question of whether this strange structure is coincidence or a sign of hidden physics we don't yet grasp. And now, lying here in the quiet, there is something soothing about realising that none of it is settled. The mystery remains. Hoag's object holds itself in the sky like a question. It asks nothing of us directly, but its form is so unusual, so precise, that we can't help but wonder why. The fact that no explanation quite works is not a flaw in science, but part of the beauty of it. Science is not about having all the answers, but about following the questions wherever they lead, even if they take us into places of uncertainty. Hoag's object lives in that place, between what we know and what we don't, a soft reminder that the cosmos is bigger than our categories. For many people, astronomy can feel distant. Light years, redshifts, halos of dark matter. These are abstract, hard to hold. But there is something deeply human in looking at an image of a galaxy like this and feeling moved. It connects us in ways that equations cannot. You don't need to understand astrophysics to feel awe at the sight of that ring, to feel the calm strangeness of the empty gap, to sense that you are staring at something unlike anything else. Hoag's object has become not just an astronomical puzzle, but a cultural icon of sorts, a picture that circulates far beyond science journals, landing in the imaginations of people who simply love the idea that the universe still holds mysteries. Lying back and thinking of it, you can picture the golden hub as a lantern, steady and calm, surrounded by a halo of youth and light, both encircled by silence. It is like an emblem of contrast, age and youth, presence and absence, order and chaos hidden beneath symmetry. It doesn't tell us what it means, it simply shows itself, and we are left to interpret. That openness is what makes it so fitting to reflect on late at night, when your mind drifts between questions and quiet. If you close your eyes and imagine being there, floating somewhere inside the dark band between core and ring, the sight would be extraordinary. The core behind you, golden and dense with stars. The ring ahead, blazing blue with youthful suns, and all around the emptiness of space stretching outward without end. It would be quiet beyond measure, silent in a way that only the cosmos can be, and yet, in that silence there would be motion. Stars orbiting, gas flowing, light streaming outward across the gulf, destined to travel for hundreds of millions of years. There's comfort in thinking about the timescales involved. The light we see tonight left those stars long before human beings existed. By the time it arrived, continents had shifted, species had risen and fallen, entire ages had passed. Our worries, our routines, our restless thoughts, they're so small against that backdrop. It doesn't make them meaningless, but it does place them gently in perspective. The universe has been at work for billions of years, and still it surprises us with shapes like Hoag's object. Whatever is pressing on your mind right now, it is lighter in that context, easier to set down for a while. And then there's the thought of coincidence, the sheer improbability of a galaxy like this forming, and of us being here to notice it. Not only did the galaxy align its structures into this uncanny ring, but another smaller ring galaxy just happened to lie behind it, visible in the hollow. The odds are staggering. And yet, here we are, looking at the image. It reminds us that improbable things happen all the time in a universe as vast as ours. Against billions of galaxies, even the rarest outcomes find a place. Perhaps we too are part of that improbability, conscious beings on a small planet, capable of looking up and wondering. Wonder is the thread that connects it all, the golden heart of stars, the blue halo of light, the blackness of the gap, the faint window within a window of the background galaxy. Each detail invites us not to solve, but to marvel. That's what makes it a perfect companion for a night like this, when you want your mind to wander slowly, gently, with no pressure to reach a conclusion. The mystery doesn't need to be unravelled tonight. It can simply be held, like a thought, like a lullaby carried across time. Astronomy often ends up circling back to us, even when it begins far away. Galaxies are not just out there, they are reflections of how we see, how we ask, how we imagine. Hoag's object tells us something about the universe, but also something about ourselves. That we are drawn to order, startled by exceptions, humbled by vastness, soothed by symmetry, and endlessly curious. It reminds us that knowledge is not just about answers, but about wonder itself, about lying awake at night and letting your mind float outward to a place 600 million light-years away, just to feel the scale of things. As you listen now, perhaps your thoughts are slowing. Perhaps you're picturing the galaxy suspended in space, the golden glow at the centre, the blue ring around it, and the endless blackness between. Perhaps you're letting the numbers fade away, leaving only the image, the feeling of distance and calm. The circle hangs there in the dark, not asking to be solved, only to be seen. And in that seeing there is peace. The stars of Hoag's object will burn for millions more years. The light they send out tonight will keep travelling long after we are gone. The mystery will remain for future generations to ponder. For now, it is enough to know that it exists, enough to let it rest in your imagination as you close your eyes. Somewhere far away, 600 million light-years across the void, a perfect ring of stars glows quietly. And here, under your own sky, you can let that thought carry you gently towards sleep. Thank you for being here, drifting with me through the mystery of Hoag's object. We've floated across 600 million light-years, wandered through golden stars and blue rings, and sat quietly in the space between what we know and what we don't. If your thoughts are slower now, softer and ready to rest, let them rest. If you found this soothing, you're always welcome to return. There are more stories waiting in the stars, more puzzles, more wonders. For now, though, you don't need to hold on to anything. You can let the galaxy fade into the background, like a distant lantern in the sky. Breathe deeply, close your eyes, and let sleep come at its own pace. Good night.